All right. Hi, everyone. Welcome to ITCS 2021, the 12th Innovations in Theoretical Computer Science Conference. Um, I'm the PC chair, James Lee. Um, let's see. Uh, I mean, it's great that we're all able to get together despite the what's going on in the rest of the world. Um, the rest of the world, the entire world. I'm excited about the program. I think this provides us actually an opportunity to sort of explore the ways of broadening participation in TCS. Like by their nature, attendance at conferences like this are limited to a small fraction of the global TCS community. So I hope that we can learn from this event in ways that sort of reshapes even our in-person conferences going forward. Let me very briefly thank the program committee for all their hard work, Umesh Vazarani and the ITCS steering committee, Gautam Kamat for helping to organize the technical aspects of a virtual conference, and the Simons Institute and their staff for hosting the event. I think briefly, Tom Gurr has some remarks to make about Safe TOC.
Yes, let me see if I can show my screen. Just 1 second. Okay, can you see the slide? Okay, good. So just want to say 1 minute about Safe TOC. So in a sentence, Safe TOC is a group of volunteers that will form primarily to combat harassment and to keep a friendly and inclusive environment. And it's great to say that ITCS is strongly committed to follow these principles. And that essentially means we want to keep the atmosphere as friendly, as inclusive as possible, and not tolerate any harassment or discrimination of any sort. For each conference, we have a few representatives. In this ITCS, it's Sumega Garg, Anna Caroline, and myself. What we want to ask of you is that if there is any problem at all whatsoever, please contact us and we will do everything within our power to help. And if you want more information, you can find it at the link below, which is safetoc.org. Thank you.
Yeah, thanks, Tom. That information is also at the program, at the top of the program, where you can also find the sort of the schedule together with the full videos that people have recorded ahead of time, preliminary proceedings, and links to the Slack channel. So every paper has a channel. I encourage the authors to check those channels to see if there's a discussion about their paper that they can participate in. And then the GatherTown map, which if you registered, you received an email about it, but you can also access it from the program page. That's open all day, including for a while after the conference, if you want to continue conversing with people. If you are graduating in the near future or you've recently graduated, there might still be some space left in the graduating bit session tomorrow morning. If you're interested in participating in that, you should contact Gautam. Again, his email is on the program, so you can find it. And then just briefly want to say this is an experiment. So it's a good idea while you're participating in a conference to think about what works and what doesn't. And we'll send out forms to collect feedback once the conference is over. And then if you're interested in discussing or hearing more about the logistics of the program and sort of forming a virtual conference on relatively short notice, then the business meeting is this afternoon at 3:30 local time, which is Pacific time, my local time. Okay, with that said, I think there is not much left to say right now. So the first session starts in a few minutes. I encourage everyone to the extent possible to have their cameras on so that everything feels more personal, helps with the sense of community. And so Yeah, so I guess in about 7 or 8 minutes, Yvette will chair the first session of the conference. Welcome again, and hopefully everything goes well.
Okay, so welcome everyone indeed. The first session will be in this Zoom room, so stick around. And we'll wait for about 7 minutes or so for people who are joining in. So in the meantime, enjoy.
So I've been wondering whether there is any chance we hear the story of ITCS and what motivated its launch.
Can you say that one more time?
Is my voice heard?
Yeah, just my sound was low. Sorry.
Okay, I've been just wondering whether there is any chance to hear the story of ITCS and what motivated its launch.
So I will defer that question to the chair of the steering committee, Umesh, who is not, but I don't know if he's here at the moment, but I'll repeat your question in the business meeting for Umesh. So he'll have a chance to answer it then.
Hey, I had a query on regarding the rooms, and in each room at a particular time slot, there are five papers that are to be presented. So, how is there a particular time slot, like 10 minutes or 20 minutes per paper, or we can ask our queries at the same time?
So it's slightly dependent on the session chair. We've given the session chair some leeway in figuring out how they want to run their sessions. But as it says in the program, the talks are 8 minutes, and then so that's 40 minutes of talks per session. But the sessions are an hour long, so there's 20 minutes in there. And then it depends on whether the session chair wants to take questions as the talks go, or they want to wait until the end and take questions as part of a larger discussion.
Cool. Thanks.
So actually, in the meantime, each of the speakers of the first session, go ahead and send me a chat message saying maybe who's going to be speaking.
Shall I go ahead and set up the presentation? Seems close. Oh, I'm the first speaker. Okay, let's go ahead and set up the share screen.
Yes, go ahead.
Oh, thanks. Oh, does this look good? Okay.
Okay, I think the time has come. Let's get this show started. So welcome everybody to the first session of ITCS 2021. This is the session on privacy and cryptography. As James said, so there's 5 talks in this session. Each one will have 8 minutes speaking, and of course there'll be a little bit of time switching in between. And also, as he said, things are a little bit experimental. So let's see how it goes. My plan is to set it up so that possibly one quick question can go after each talk. But the majority of the questions, save them until the end, and we'll have an open time and you can address for each of the different authors. Okay, so the first talk in the session is on distributed differential privacy and counting distinct elements. This is a work, also I should say, I saw all the names in this session are going to be quite the exciting challenge, so I apologize in advance. So this is by Li Chen, Badi Ghazi, Ravi Kumar, and Pasin Manurangsi, and Li will give the talk.
So hi everyone, I'm Li Chen from MIT. Thanks for joining me here today. I'm super happy to present my joint work with Badi, Ravi, and Pasin from Google Research. So since the talk is on differential privacy, let us start by recalling the definition of differential privacy. Suppose we have an algorithm M runs on a data set D consisting of n elements x1 to xn and produces a probabilistic output n of D. And we say 2 data sets are neighboring if they differ by at most 1 element. And we say an algorithm M is epsilon delta differentially private if for all pairs of neighboring data sets D1 and D2 and all possible events E, the probability of E happening under D1 and D2 differ by a multiplicative factor of E to the epsilon with a small additive tolerance delta. This definition is beautiful, but it does not entirely address the concern of privacy in the distributed setting. In such a setting, each user holds their own data xi initially. To naively implement the above algorithm M, they have to send their raw data xi to a single curator, and then the curator runs the private algorithm M on the collected dataset D. The important issue here is that after sending your raw data to the curator, you have to trust their integrity for the rest of your life. And sometimes this may not be a good idea because the database could be hacked and your information could be lost. So the local model in the differential privacy is proposed to address the concern of that users may not want to trust the curator. Instead of sending their raw data to the curator, they first apply a randomizer R on their data xi, and then send the output of the randomizer to the curator. And we use the transcript to denote everything the curator sees with dataset D. Here, in the local model, the transcript is just a concatenation of all the messages rx1 to rxn. And the curator just runs the algorithm on the transcript. The privacy requirement now is that even the curator cannot learn anything about a single user. So in the same spirit, we can define the epsilon delta differential privacy in the local model as follows. So definition is basically the same. This looks good, but it also comes at a price. As we'll see later, to achieve the same privacy, algorithms in local models sometimes perform much worse than their counterparts in the central model. So motivated by the drawback of the local model and the central model, the shuffle model aims to provide better utility while putting as little trust as possible on the curator. This model is an additional layer of a shuffler, which applies a random permutation on all the messages sent by the user, and the curator runs on the shuffled version of all the messages without knowing which user sent which messages. So in other words, it anonymizes all the messages. Again, we define the transcript with ∆z as everything the curator sees in a protocol. Here, the transcript is the output of the shuffler, which is a random permutation of all the messages RXIs. And the curator runs on the transcript. Similarly, we can define the epsilon delta differential privacy in the shuffle model as well. We note that similar to the local model, here we put no trust in the curator, but we do put additional trust in the shuffler by assuming it correctly performs the random permutation. Therefore, the privacy can go through. So to compare these models, a great example is the basic aggregation problem, where each user gets a single Boolean bit, and the goal is to estimate the sum with constant epsilon while polynomial differential privacy constraint. As one can see, we have a spectrum of trust in the curator and also a spectrum of the utility. Here is the arrow. And the great thing about shuffle model is that for this basic problem, it can achieve constant error by only putting additional trust in the shuffler. Therefore, it cannot achieve the best of the both worlds for this problem. And in this talk, we'll study the problem called count distinct problem, which is another basic problem in the distributed setting. So there are n users, each holds their own data xi, and the goal is to estimate the number of distinct elements among x1 to xn under the constraint of being epsilon delta dp. In the central model, the problem is very easy, and you can achieve constant error. And we first show that not only for constant epsilon, in fact, for some d equals n by polylog n, for lim d epsilon, the problem is still nearly maximally hard, as it required n by polylog n error in the local model. And surprisingly, we further show that if we further increase epsilon from lim d to lim n, then the problem suddenly becomes very easy. It can be solved with error root n comparing to nearly n. Note that lim d equals lim n minus or log n. So it is very close to lim n. And for the shuffle model, we first show that for constant epsilon and the inverse quasi-polynomial delta, count distinct is nearly maximally hard for the single message shuffle model, in which everyone can send at most one message. And next, surprisingly, we show that if we allow each user to send at most half plus little 01 messages in expectation, instead of being worst case, then the problem can be solved by shuffle protocol with square root n error. Therefore, there is a big gap between messages in worst case and the messages in expectation. And note that the count distinct problem has global sensitivity 1. So our result implies a 1 versus near linear separation between global sensitivity and error in local and shuffle model. This answers an open question. We also obtain a 1 versus near linear separation between global sensitivity and error in two-party differential privacy, and answer another open question. And check the paper for more details on this part. And finally, we obtain some new lower bounds for other problems in the shuffle model. The selection problem is defined as follows. So there are n users. The S1 gets a d-dimensional preference vector. And for for index j, the score of j is defined as the expectation of xij. And the goal is to find out j star such that the score of j star is close to maximum. And we show that for constant epsilon, 1 over n delta differential private shuffle protocol with at most k messages from each user cannot solve selection if n is at most d by k. Our result is similar to our recent independent work by Cho and Alman. They study a more restricted version of shuffle model called the robust shuffle model, and they prove that for unbounded messages, such models still cannot solve selection if n is at most root d. So let me conclude with some open problems. So the first question is, can we prove lower bounds for unbounded messages in the shuffle model without the robustness constraint? As you can see, their lower bounds require the robustness condition, while all lower bounds do not work for unbounded messages case. And also, can we extend the single message shuffle lower bound for distinct to the region that delta equals 1 over polynomial? All lower bounds requires delta equals 1 over quasi-polynomial. So that's an open question. Thank you. That's all.
Okay, thank you very much. So actually perfect timing on the talk. Excellent. So let's take a quick question while the next speaker is setting up. So Salil.
Hi, Lee. Can you say anything about the techniques in the lower bounds? And in particular, do you identify a hard distribution of inputs for these problems, for the count distinct problem?
Yes. So actually, the lower bounds we use the lower bound techniques for proving lower bound of the estimate the unseen problem in the literature of property testing. So here we use something called moment matching. So we construct two random variables with matched moments, but one variable is mostly 0 and one variable is mostly non-zero. And then we use these two random variables to construct two very different distributions. They behave similarly, their moments behave similarly, but somehow the number of distinct elements differ dramatically. And then we show that local algorithm cannot distinguish this based on some personalization trick. I mean, it's a high level idea. The lower bound itself is pretty complicated. Yeah.
Great, thanks.
Yeah, thanks for the question.
All right, perfect. So Nikita, go ahead and claim the stage here.
Oh, sorry, could you stop sharing? Sorry, I can. Okay, thank you.
Sorry.
So, may I start now?
Okay, excellent. So in a second. So the second talk will be on basing auxiliary input cryptography on NP hardness via non-adaptive black box reductions. This is work by Mikito Nanashima, and indeed he will be giving the talk.
Yeah, thank you. So, okay, my name is Mikito Nanashima. So, yeah, today I'm going to talk about this topic. Okay, let's begin with the introduction. So this work is related to these two fields, worst case hardness in complexity theory and cryptography. And as you know, there's a huge gap between these two fields. And one of the most challenging questions is to construct one-way functions based on the hardness of NP problems, in other words, to show this direction. So, and very natural approach, a very basic approach to show this direction is to construct a reduction from solving some language L to inverting some function f. And if this L is NP hard problem, then we can show the control position of the above result. But to construct such a reduction, there's a specific barrier on the types of reduction. That is non-adaptive black box reduction. So, and so in this setting, this type of reduction looks like this figure. And the key part is, so yeah, This reduction accesses adversary for inverting F as a black box as an oracle, and it makes its queries parallel or in one round. And this is a very simple and familiar form of reductions. But unfortunately, the previous work showed that if we can get such a simple reduction for this problem, then we can show this result. And the point is that so if L is NP-hard problem, then this implies a collapse of polynomial hierarchy. In other words, under the very reasonable assumption on polynomial hierarchy, we can exclude such an attempt. And this previous work gives us very important directions, developing non-black box techniques or adaptive techniques. But in general, to construct such a somewhat complicated techniques seems to be very challenging task, especially for this program. So that's why in this work, we try to suggest the third choice, that is to change the goal. Or in other words, we try to get intermediate cryptographic primitive instead of standard cryptography. And our focus of this work is auxiliary input cryptographic primitives, which was originally introduced by Ostrovsky and Wigderson. And this type of primitive is not one specific function, but defined as a family of functions indexed by binary strings, and which has a weaker security condition that for each polynomial adversary, so depending on this A adversary, there exists a secure path for adversary. And this is very natural intermediate model between usual worst case hardness and average case cryptography. And breaking such a auxiliary input cryptographic primitives can be formulated as a kind of worst case of average case problem. That's why, yeah, we cannot apply directly the previous work on non-adaptive black box worst case to average case reduction to this case. That's why the important question is, if we try to get such a intermediate cryptographic primitives, then are non-adaptive black box reductions sufficient? And we address this issue in this work as a first step for such a study on intermediate primitives. Okay, now let's see our result. Again, our goal is to consider the following question. If we have some non-adaptive black box security reduction from here to AI primitive, breaking AI primitives, then what happens? And in this work, we consider three fundamental types of AI primitives: pseudo-random generator, one-way function, and heating set generator. And roughly speaking, the relation among them is like this. And so the first result is the following. So if we can get a non-adaptive black box security reduction from here to breaking auxiliary input pseudo-random generator, then we can also show the collapse of polynomial hierarchy. So that's why we can exclude this part. And we also consider these two cases of auxiliary input one-way function and auxiliary input heating set generator. And the reason why we consider these two cases separately is, as far as I know, the currently known security reduction from the second primitive to first primitive uses some adaptive techniques. So we cannot translate this type of black box reduction into the first one. So we consider these two cases separately. And the second and third result is the following. So if we can get non-adaptive black box reduction, then in fact, we could not show the strong consequences like the kind of collapse of polynomial hierarchy, but we can still surprising consequences. So we can extend this non-adaptive black box reduction to one-way function which has infinitely open security, be adaptive black box reduction. In other words, we can get NP-based one-way function. And in fact, this is not strong to exclude such a non-adaptive black box reduction, and it has two opposite interpretations. So negatively speaking, this can be regarded as a hardness result for getting such a non-adaptive black box reductions. But positively speaking, this can be also regarded as a new approach for NP-based one-way function, because to construct one-way function, all we have to do is to construct primitives via very simple security reduction. And that's why, so I guess the important question, future direction, is to verify the validity of this positive perspective. And I will share with you more two directions. So first one is to consider other cases where such intermediate primitives or intermediate primitives can be helpful for constructing NP-based one-way function. And second direction is, yeah, of course, there is still possibility that this non-adaptive black box reduction implies a collapse of polynomial hierarchy. That's why the second direction is to exclude such a non-adaptive black box reduction, especially for the case of auxiliary input one-way function. Okay, finally, let's see proof ideas very roughly, and this is a very rough map for the proof. And for the first result, the key part is to show this part, non-adaptive black box reduction from here to some average case problem. Then we can get non-adaptive black box worst case to average case reduction. Then by applying the previous work, we can show the collapse of polynomial hierarchy. And in fact, this reduction is also very simple reduction. And the proof for the second result here is, I guess, the key part of this work. So roughly speaking, first we translate auxiliary input one-way function into auxiliary input pseudo-random generator by using the standard cryptographic technique. Then we apply this non-adaptive black box reduction in assumption again here. Then we can construct adaptive black box reduction from NP-hard language to breaking IO one-way function. So this is very rough explanation. And for the third result, we applied the universal expression technique to translate this type of non-adaptive black box reduction into non-adaptive black box reduction from NP-hard language to breaking auxiliary input one-way function. Then we can apply the second result again, and we have adaptive black box reduction from NP-hard language to breaking one-way function. That's why we can get the third result. Okay, that's all. Thank you for your attention.
Actually, just a quick question while the next speaker is setting up. So maybe you can close the share. So the next, no problem. What is it? Can you describe a little bit? What is the dist NP?
Sorry, this means distributional NP problem. So yeah, it is an NP problem, but the instance is generated according to some fixed Poisson-probable distribution.
Got it, thanks.
If you have time for one more query.
Sorry, go for it.
Yeah, I would like to ask, what were the pseudo random number generating algorithms that you used, and why were it not feasible in your setup?
So sorry, could you say it again? So I could not understand.
Yeah, with respect to the pseudo number generations, why were it not feasible? Why was it not feasible? Because you said no, in your graph that you drew, you had if you go back to the slides.
I think the question is about that it's adaptive, that the constructions of PRG from one-way functions are adaptive, so your impossibility result didn't extend. I think that's the question.
Yes, yes.
Sorry, could you say it? Okay, sorry. Sorry.
I think he's asking, you had an impossibility result about PRG.
Mm-hmm.
And you said it doesn't extend. You had three boxes, and he's asking why didn't it extend? Because, because it's adaptive.
Yes. So
were there any bounds?
You mean so? Yeah. So you mean sorry. So for the second result for auxiliary to one function, it can be translated black box reduction from breaking pseudo-random generator. But then why it implies the collapse of polynomial hierarchy? That is your question.
Yes, and why did it
that's
collapse?
Why, that's why. So because as far as I know, all of known security reduction from breaking auxiliary input one-way function to breaking auxiliary input pseudorandom generator uses adaptive technique. We do not know no adaptive ones. That's why if we translate no adaptive black box reduction from language L to breaking AI one-way function into sorry, breaking pseudo-random generator, then we lose the no adaptiveness. That's why we cannot apply the first one.
Okay, yeah. Okay, thanks.
You know, so if we can get very simple security reduction from auxiliary input one-way function to auxiliary input pseudo-random generator, then we can also exclude the attempt for auxiliary input one function and auxiliary input heating generator.
So it's not easily extendable. Yeah. Okay. Got it. Thanks.
Thank you.
Actually, in the meantime, we're having some technical difficulties here, and let's see if we can get this fixed.
Can you hear me?
Yes, we can hear you.
Okay. Maybe I will try sharing again. There was some issue.
Yeah, go ahead and try.
It says my screen sharing is paused, but can you see my screen?
It just says that you have started sharing your screen.
Oh, okay. I'm clicking on resume share and nothing is happening.
Are you sharing your desktop or just the application?
Just the application.
Would you mind sharing your desktop and then opening the application within that?
Okay, sure. Yeah. So, and I don't, okay, entire screen, right? Yeah. Is that, okay, great. Now it's fine, right?
Yes, we just need to
excellent.
The presentation mode and then.
Okay, great.
Great.
Okay. Maybe I'll start.
Good success. Okay, so the next talk will be on query complexity lower bounds for local list decoding and hardcore predicates. This is a work by Noga Rondvi, Ronen Chaltiel, and Nitin Varma. And Nitin will be giving the talk.
Hi, I'm Nitin Varma. I'm a postdoc at the University of Haifa, and I'll be talking about query complexity lower bounds for local list decoding and hardcore predicates. I'll first briefly define list decoding, local list decoding, and briefly tell you about our results and applications of our results to black box proofs for hardcore predicates. I will conclude with some open problems. A binary code is half minus epsilon L list decodable if for every word W, there are at most L messages whose encodings are close to W, in the sense that the distance between the encodings of these messages and W is at most half minus epsilon times N. Or in other words, for every word, there are only very few code words in the code that are close to it. Now, list decoding has a lot of applications in theory CS, and this has also been generalized to sublinear time algorithms as local list decoding. And the goal here is to recover each coordinate of a desired message from the list locally in sublinear time. And a more formal definition is like this. For every word and every message M, such that the encoding of this message is close to the word. So you want to basically, when you're given query access to the word, there exists some advice that your algorithm gets such that for every message coordinate, you output the bit cut of the desired message at that coordinate with probability at least 2/3. And we study local list decoding of very low rate codes. A candidate example is the Hadamard code. And Hadamard code has very efficient local list decoders. A seminal result by Goldreich and Levin gives local list decoders with list size and query complexity 1/epsilon square for the Hadamard code. And the question that we ask is whether the query complexity can be improved, say 1/epsilon to the little of 1, if we allow for very large lists. Now, the motivation comes from the fact that improving this upper bound has the potential to obtain better hardcore predicates based out of one-way functions. Now, here are our results. For large epsilon, we show that the query complexity of local list decoding is 1/epsilon square omega. And this is a tight lower bound as evidenced by the upper bound by Goldreich-Levin. And our lower bound holds for large list sizes, and in particular also for codes of very low rate. Okay, so for codes for very low rate, this is also the first lower bound even for small list sizes. And our result extends and improves the result of Greenberg et al. That worked for codes with larger rate. In particular, the result of Greenberg et al. Did not apply for Hadamard. And for smaller epsilon, we show a lower bound of omega root of 1 over epsilon. And together, these rule out the upper bound of 1 over epsilon to the little of 1, and even for very large lists. And here are some consequences of our results. So Goldreich-Levin theorem can be restated in terms of obtaining hardcore predicates. Suppose you have a very hard one-way function that for circuits of size S, it is hard to invert the function f with probability more than rho. Now, based on this f, you can define a new one-way function f nu and a predicate f pred such that for all circuits C prime of size S prime, which is only smaller than S by a factor Q, where Q is the query complexity of Hadamard, local list decoding Hadamard, you can say that like for a random input, if you only have access to the evaluation of f nu on this random input, your circuit cannot compute the evaluation of f pred, the predicate on this random input, with advantage of more than epsilon over random guessing. Now, concretely, assume you have a circuit, you have a hard function that cannot be inverted by circuits of poly size with probability 1 over poly k. Then Goldreich-Levin assures that you can obtain a hardcore predicate with that cannot be guessed with an advantage of less than 1 over poly k. Now, even if the original function you start with has a much stronger hardness, this is all that Goldreich-Levin can give you. And the first question we ask based out of these results is whether it is possible to obtain a much stronger hardcore predicate, maybe by replacing Hadamard with another locally list decodable code. And so we prove that no, it is not possible. And the proof is an extension of the proof for the small epsilon case. Now, we also ask something much more general. So we ask whether maybe it is possible to obtain a hardcore predicate, a stronger hardcore predicate, via some completely different black box kind of method. And we again show that no, so we define a general class of black box methods for obtaining hardcore predicates and show that no, so you cannot really get very strong hardcore predicates by black box methods. And here are a bunch of open problems. So one would be to improve the lower bound for the small epsilon case from 1 over root epsilon to 1 over epsilon square, the tight lower bound. Now, our lower bound for the large epsilon case can be extended to decode from 1 minus epsilon fraction erasures, and not errors, erasures, to get a bound of 1 over epsilon. Is it possible to do a similar extension for the small epsilon case? So far, we don't see how our techniques would directly extend, but is it possible? Now, so we only ruled out black box techniques for obtaining stronger hardcore predicates from hard functions, but maybe there are non-black box techniques that can help obtain stronger hardcore predicates from hard functions, and can we do something here? And thank you.
Thank you. All right, is there any quick question while we move to the next talk? Actually, if not, then I have a quick question. So when you say black box, this is black box in what? And can you say very briefly about what kind of more general form of black box reductions you guys prove things about?
Yeah, so in the sense, so we say that a black box reduction can be thought of as a pair construction and reduction. So construction will map a hard function to a new one-way function and also a predicate. And we do not assume that this map construction is efficiently computable or anything. And the reduction so gets Oracle access to my hard function and also some other function H that claims to invert my hard function efficiently, right? And additionally, the reduction can also be non-uniform. So it can also get some advice that depends on both the hard function and also the inverter, in a sense, right? Yeah, so this is the generic setup. I don't think I missed out anything, but yeah, more or less. But of course, there are more details. There are, yeah.
Good.
Thanks.
All right, thanks. So Silvash, the next speaker, can set up. Excellent. The next talk will be on lower bounds for off-chain protocols, exploring the limits of plasma. This is a work by Stefan Jandowski, Gregor Fabianski, Sebastian Faust, and Silvash Riahi. And Silvash will speak.
Yes, so can you hear me? Yes? No?
Yes, we can hear you.
Yes,
Okay, perfect.
Yes.
Sorry. So, hello everyone. My name is Silvash Riahi, and today I will present the paper Lower Bounds for Off-Chain Protocols, Exploring the Limits of Plasma. This is a joint work with Stefan Jimbowski, Grzegorz Fabianski, Sebastian Faust, and me, Silvash Riahi. Stefan and Grzegorz are from University of Warsaw in Poland, and Sebastian and I are from TU Darmstadt in Germany. So, let's start with some motivation. We as humans need to maintain ledgers or logbooks for many different applications, such as trading, legal agreements, banking, and so on. And traditionally, trusted entities, such as the stock market, notaries, or banks, maintain these logbooks or ledgers for us. However, recent events have shown that these trusted entities are not really trustworthy. For example, there's a scandal regarding a company called Wirecard in Germany's stock market, or we all remember the 2008 housing crisis, which interrupted the global markets quite substantially. And people have been thinking, well, how can we make these trusted entities behave honestly? Well, some say that we can achieve this via more transparency, such that we can detect malicious behavior sooner, but others have been trying to get rid of this trusted entity altogether. And one of the proposals to do so is blockchain technology. And I want to point out that there's a huge realistic and sometimes unrealistic hype around blockchain and technologies related to blockchain. And this work also tries to make the expectations from protocols run over the blockchain to become more realistic. But what is blockchain? Well, blockchain's core is basically a consensus algorithm, which is run between a set of parties, and as long as more than half of the parties participating in this consensus algorithm are honest, they can agree on the latest state of the system. However, consensus algorithms, large-scale consensus algorithms, are expensive. And that's one of the reasons why blockchain technologies do not scale. For example, Bitcoin can process around 10 transactions per second, while Visa payment system can process up to 50,000 transactions per second. This is quite a huge gap here. And people have been thinking and proposing solutions in order to improve blockchain scalability. And one of the more recent proposals, and also the focus of this work, is off-chain protocols. And by off-chain, I mean that parties only communicate with the blockchain if it is necessary, and they try to keep their communication with the blockchain to a minimum. More specifically, we analyze a class of off-chain protocols called plasma protocols. So what is plasma? Well, plasma was first introduced by Poon and Buterin in 2017, and in the literature, it is also referred to as commit chain. The main idea of plasma is as follows. We have an operator, and parties, instead of communicating with a blockchain and submitting their transaction to the blockchain, they submit it to this operator who gathers these transactions, and he periodically timestamps the latest state of the system on the blockchain. More specifically, the operator is basically maintaining his own ledger L. He publishes the content of L off-chain, for example, on his web page, and periodically timestamps this ledger L by publishing the hash of L on the blockchain. By using this hash of L, parties can later refer to it and then prove that, oh, they own some amount of coins in the system. So as you can see here, we are trying to minimize the communication with the blockchain. So it's an off-chain protocol. Let me continue with an example. Assume that Li is the latest state of the system where Alice owns 1 coin, Bob coins 0 coins, and Charlie owns 1 coin. The operator uses the hash function to hash this table and publishes just a hash over the blockchain. This idea can further be improved using Merkle trees, but I will ignore that for the purpose of this talk. So the total balance of the system at this point is 2. Now Alice can send 1 coin, for example, to Bob, and the state would be updated as follows. Bob will have 1 coin, Alice will have 0 coin, and Charlie will have 1 coin. And this can go on. Now, this idea can also be extended in order to allow deposit and withdrawing assets directly to and from the blockchain to this plasma system using the monetary capabilities of the blockchain. But this solution has a drawback. And the drawback is as follows. The operator can always withhold this state and not publish it to the users. This is called the data unavailability attack. And I will get back to this more in a few seconds. All in all, there are 2 main categories of plasma protocols. One is plasma cash, where users own tokens similar to a cash. So we are assigning tokens to users. And another version of plasma is fungible plasma, where users have accounts similar to checking accounts, and we are assigning balances to users in this system. Now, our contribution is as follows. We show that there is no perfect plasma protocol out there. More specifically, we show that either protocols fall under a situation like plasma cash, where exiting assets from the plasma system to the blockchain requires huge communication with the blockchain, or we are in a situation like fungible plasma, where the system suffers from a phenomenon called non-uniquely attributable mass exits. And we cannot achieve the best of both worlds. Now, what is non-uniquely attributable mass exits? By non-uniquely attributable, I mean that no judge can decide who is malicious, the accuser or the accused. And this directly relates to the data unavailability attack, because data unavailability has non-uniquely attributable faults. Although I will not really go into the details here in this short talk. And what is mass exit? Mass exit means that honest users must withdraw their assets before it is too late, otherwise they might lose all their coins. And this is quite substantial, because if everyone tries to exit their coins at once, then the blockchain would be overloaded, and again they have to communicate a lot with the blockchain. So I would refer you to the full presentation and our paper for more details regarding how our proof works, how our modeling works. But here I would like to give a sneak peek on the main idea behind our proof and our result. So I will continue with our previous example. Alice has transferred 1 coin to Bob. And now at this point, the operator withholds this latest state, Li plus 1, from Charlie, who is the honest party here. At the same time, Alice reverts her state internally to what it was in Li. So she will claim that she has 1 coin and she has never made a transfer to Bob. Note that Charlie is completely unaware of what has happened between Alice and Bob in this state. Now, Bob tries to exit from the system. This is completely legal exit. He owns actually 1 coin in the system. He should be able to withdraw it. After this exit, the total balance of the plasma system would be reduced by 1. So the total balance would be 1 because Bob has exited 1 coin. So we would end up in the following situation. Alice claims that she has 1 coin, Charlie has 1 coin indeed, and Bob is gone. But there is only 1 coin in the system. So what would happen if Alice exits? Well, Charlie then would not be able to exit his coin because there is not enough balance left in the system. How can we prevent Alice from exiting? Well, either it must be clear from Bob's exit that Alice cannot exit. This means that Bob's exit must contain enough information in it that you can identify people who have actually transferred coins to Bob. So Bob's exit would be large. And the other situation would be that Charlie must exit before Alice. So we would end up in this mass exit situation, which I pointed out before. Now this is just the main idea behind our results. And there are a lot of details that I've just ignored here, but for those I would refer you to the paper and also the long version of the presentation. So with this, I would like to conclude. In this work, we for the first time initiated the study of lower bounds for off-chain protocols. And we show that there is an inherent separation between plasma cash and fungible plasma. So you cannot achieve the best of both worlds, which were the focus for many years for many of the people working in this area. And both plasma variants have their place and use case in practice. So if you have an operator who is probably semi-trusted, then fungible plasma is the way to go because it would be much cheaper if parties want to exit. But on the other hand, if the operator is not trusted, well, maybe plasma cash would be better. Now, let me point out some future works. Well, we just initiated the study of analyzing lower bounds for off-chain protocols, and there are many different classes of protocols that can be analyzed here: channel networks, virtual channels, and so on. Furthermore, one can try to improve our results or try to analyze them by trying to remove some of the modeling assumptions that we make, or trying to see if the results would go through if the modeling is different. With this, I would like to thank you all for your attention. And if you have any questions, feel free to ask, contact me or any of the co-authors. Thank you very much.
Okay, since it's
been
a little of... Oh, go for it. We'll take one question.
Just the complexity bounds with respect to those new operations that you have introduced. Does that have a effect on the versus the vanilla chains?
Oh, I'm not sure exactly what you mean by the operations that we introduced. You mean the depositing and exiting, or?
Yes, the three, depositing, exiting, and one more operation that you had with respect to the chaining.
So basically, a plasma protocol must have all of these operations: depositing, exiting, and making transfers off-chain. Because otherwise, if you can't deposit and withdraw assets, you're basically timestamping some information on the blockchain. So it is not really that useful. So our lower bound indeed is regarding the communication complexity required with the blockchain in order to allow users to exit their assets from off-chain to on-chain and being able to use it.
Oh, okay, cool, thanks.
No problem.
All right. We'll move now to the final talk in the session, which is about black box uselessness, composing separations in cryptography. This is a joint work between Geoffroy Coteau, Poyef Rashim, and Mohamed Mahmoudi. And Geoffroy will give the presentation.
Yeah, thanks a lot. Everyone can hear me well? Good. So I'm Geoffroy. This is a joint work with Puya and Mohamed. And in this work, we try to take a fresh look at the notion of black box reductions that you've heard about already quite a few times in this session. So let me briefly recall the basics. We're looking at cryptographic reductions. So that's an area of cryptography where we try to prove statements of the form: if primitive A exists, then primitive B exists. And that's very useful because at their core, essentially all or most of our cryptographic primitives rely on unproven assumptions, like assuming P not equal to NP. So proving such reductions simplifies the crypto landscapes and allows us to derive new connections between primitives and to achieve new constructions. So reduction-based cryptography enjoyed many celebrated successes in the past. For example, in the area of private key cryptography, a sequence of celebrated results in the 90s have managed to show that essentially all private key crypto primitives are equivalent. So stream ciphers, universal hash functions, commitment scheme, they can all be reduced to the existence of one-way functions, the most basic object of cryptography. However, there are countless cases where we do not know of such reductions. And that's typically the case when we try to base the existence of public key cryptography, for example, on private key cryptography. So can we construct key agreement out of one-way functions? We don't know. And that's a bit unfortunate and annoying, because we believe key agreement exists, we believe one-way function exists, so there has to be a reduction. And the reduction could be, well, ignore the one-way function and build the key agreement from scratch. So this lack of reduction has to be a limitation of our techniques. So the core insight in this area was given by Impagliazzo and Rudisch in 1989, and it's the following. Most cryptographic reductions that we know of are black box in the sense that they are oblivious to the specific implementation of the source primitive and of the adversary. So the slightly more formal definition is that there is a black box reduction from a primitive B to a primitive A if we have a construction and a reduction. And the construction should be such that it's a construction of B, which should be efficient whenever we have an efficient implementation of the primitive A, and secure whenever we have a secure implementation of the primitive B, in the sense that we have a reduction from having an adversary against one to having an adversary against the other. So, but let's just stick with black box reduction, or a large set of techniques for reduction that do not precisely look at at much more than the input-output behavior of the primitives involved. And so the seminal result by Impagliazzo and Rudisch was that there is no black box reductions from key agreement to one-way functions. And since in this seminal result, there has been a tremendous number of black box separation between cryptographic primitives, and they explain why we've been stuck for so long at some problems we're trying to solve, but they also guide future constructions by ruling out a large class of methods. However, there are still some limitations of our black box separation results. And one of them is that a black box separation on, say, between a primitive A and a target primitive P only rules out the possibility of constructing P from A in a black box way, but using A in isolation with nothing else out there. So in particular, it does not say anything about the possibility that we could build P in a black box way from two primitives A and B, even if A alone or B alone are black box separated from P. So in a sense, we do not have any way to compose our black box impossibility results to derive stronger black box composability results. And that's unfortunate, because in crypto, we do that all the time. We take a bunch of cryptographic primitives and assumptions, we sort of mix them together, and we obtain new cryptographic primitives. And if we want to prove limitations for black box construction of these types, then currently the only thing we know how to do is, say, proving black box separation for all subsets of the cryptographic primitives that we might want to consider. So can we do better? Well, in our work, what we do is exactly try to introduce a notion that allows to have this composition, and we call it black box uselessness. Informally, a primitive A is black box useless for building another primitive P if for any auxiliary primitive Z, if we have a black box construction of P from A together with Z, then we must already have a black box construction of P from Z alone. If we have black box uselessness, then we have a natural and easy composition theorem, which says that if A is black box useless for P and B is black box useless for P, then the joint primitive AB has to be black box useless for P as well. Why? Because since A is black box useless for P, if we have a construction from ABZ, we can remove A, seeing BZ as the auxiliary primitive Z prime, and then we can apply the black box uselessness of B to remove B, which proves the black box uselessness of the joint primitive. So that's easy. So in our work, the main contributions are fourfold. First, the definitional framework. We introduce this notion of black box uselessness, identify various flavors, we cast them in the framework of black box reduction, by Reingold, Trevisan, and Vadan, and we formally prove this composability theorem that I briefly mentioned on the previous slide. And we also show that a large class of black box separation methods that have been used in the past, which is called the compiling out paradigm, satisfies an interesting property in general, which is that this compiling out techniques still works even in the presence of an auxiliary oracle Z. So in a certain sense, it relativizes. And this means that we can directly turn results in this framework into black box uselessness results. So we get kind of for free a large number of black box uselessness results by importing a result from the literature. Then we look at what's probably the most fundamental question we could ask in this area, which is whether one-way functions are black box useless for key agreement, or whether we could use them in a black box way to build key agreement together with other primitives. And we prove the following preliminary result. One-way functions are black box useless in any unbalanced construction of key agreements, which are all construction of key agreements where one of the parties makes only a constant number of queries to the one-way functions. We also prove a number of related results for restricted cases. And finally, we also look at the complementary landscape of black box helpfulness and put forth a conjecture regarding the black box helpfulness of one-way functions for building collision resistant hash functions, but I won't have time to tell more about it. So before I leave you, just a quick glimpse on kind of the main question we look at, which is whether one-way functions are black box useless for building key agreement. So we start from the Impagliazzo-Redish black box separation between one-way function and key agreement. We observe that this attack, so it's an attack against any key agreement that builds on one-way functions in a black box way. This attack fails in the presence of an auxiliary oracle. However, the crucial idea is that we can make the following case distinction. Either one-way functions exist relative to this auxiliary oracle Z. Then that means that we can build our one-way function from Z in the first place, so we don't need the one-way function in our black box construction, and the already implies a key agreement. Or there are no one-way functions relative to Z, so we have a one-way function inverter, and we managed to use this one-way function inverter to make the Impagliazzo-Redish attack efficient even in the presence of Z, up, of course, to some caveats I'll let you see in the papers. And so that's the essence of the proof. There are a bunch of open questions that stem from our work. One of the main one is, can we extend our result to all key agreement protocols? We conjecture that the answer is yes, but we could not prove it. And that concludes my talks. Thank you for your attention, and I'd be happy to answer any question.
I have a quick question. Can you tell me which type of key agreement this doesn't work for? Like what is balanced or unbalanced? I didn't get it.
Yeah, so unbalanced key agreement means one of the parties will only make a constant number of queries to the one-way function in the protocol. So it only makes a very small, like restricted use of the one-way function. Both parties can make an arbitrary number of calls to the auxiliary primitive Z. So that's...
So in particular, if both parties only call the one-way function constant number of times, your separation works.
Yes.
Your not separation, your result that it's useless works.
Yes, exactly. But the dream result would be that both parties can query the one-way function arbitrarily many times. And in this setting, we only manage to rule out miracle type key agreements, which is where essentially everything is simultaneous. We send a single message, we start making queries, and we do not make queries when computing the output after receiving the other party message. So this miracle type key agreement, there we can rule out key agreement even with an arbitrary number of queries, but there we impose a restriction on the structure.
Got it. Thank you.
But does that rule out traditional public key cryptography?
So no, it does not rule out traditional public key cryptography. Otherwise, we might have been more cautious with stating our results. So
no, I meant
so different exchange does not make the black box use of a one-way function. It's a direct construction. So it's a direct construction from a specific number theoretic problem. So traditional public key cryptographic.
I'm sorry, I meant if this agreement protocol is based on a public key encryption function. So rule out a reduction that uses a one-way function and another primitive to construct a public key encryption system.
Sorry. Yes, we do roll out. So you can. So what we were at construction of key agreements. So these key agreements, they have restrictions. So if you extend that to the setting of public key encryption, what we roll out is the construction of public key encryption that will not make query to the one-way function when invoking the decryption or the decryption function. So we rule out the possibility of having public key encryption that makes any queries in the encryption, but no queries to the one-way functions in the decryption, but possible queries to the other primitive, or where the encryption would only make, one of the encryption or decryption would only make a constant number of queries. This is the kind of thing that we roll out. Does that answer your question?
Yes, thank you.
Wait, doesn't the second thing, like the first thing was 0 calls to the one-way function and the decryption, and the second thing was constant in one of them. Doesn't that imply, isn't the first case a special case of the second?
I realize that at the same time as saying it. So if I get,
there is also key generation. There is also key generation. So when we say one party asks a constant number of queries, key generation and decryption happen by the same side.
Got it. But if both key generation and encryption is not constant, it's still good, and as long as decryption is 0.
Yes.
Yes.
Got it. Thank you.
Thanks, Mohammed.
Okay, just a moment before other people jump in. So at this time, the next session it will be starting in about a minute. So if you really want to go to those talks, feel free to go ahead to the second Zoom link. However, we are able to stick around, and I'd like to open the floor, I suppose, to questions to any of the authors. So let's go ahead, maybe if it becomes chaotic, and you can use your Zoom hand raising.
So I wanted to ask about the last talk, Posel. So if I don't know if Jeffro maybe can put the slide. So for collision-resistant hashing, do you have an assumption which is maybe unnatural but easy to state, which you think is black box separated from collision resistance, but with one-way function, is sufficient, right?
Okay, for collision-resistant hash function, we don't have we only have a conjecture, but our conjecture is that they are useful for building collision-resistant hash functions, and intuitively, the auxiliary primitive is the Simon oracle. So the idea is the following: Simon oracle. So this very weird kind of one-way permutation, but where you can sample collisions alone, it does not give you a collision-resistant hash function.
Actually, can you explain again, what is this thing?
Yeah, so what we want to show is that one-way functions are helpful for building in a black box way collision-resistant hash function, even though they are black box separated from them. So to do that, we have to exhibit an auxiliary primitive, which is separated from collision-resistant hash function.
Yes, I need to explain the specific primitive.
So the specific primitive is something that would be essentially Simon's oracle, meaning a one-way permutation, but where you have a collision sampler. So like you have something that allows you to sample collisions. And it's not exactly a primitive, so it's a bit all about formulating exactly what we mean there, but it's a bit technical. But at very high level, this primitive we know does not black box imply collision-resistant hash function. That's Simon's result. However, if you use, say, 2 instances of this primitive together, like this together with a one-way function, at a high level, it seems to imply a collision-resistant hash function by using the Holmgren-Lombardi result. So the Holmgren-Lombardi result says that if you have 2 one-way functions simultaneously and you have some strong kind of amplification results, like inverting both of them happens with probability much smaller than inverting a single one of them, then this implies collision-resistant hash function. So you can reduce the conjectures that one-way functions are black box helpful for collision-resistant hash functions to some conjecture about how one-way functions amplify in the presence of a random oracle, such as Simon's oracle. That's kind of the reduction we have. So the question is, let's give a simple formulation of the question. I give you a one-way function and a random oracle, and the random oracle was sampled independently of the one-way function, and now you need to invert both. Can you prove that inverting both of them simultaneously, your probability of succeeding at doing that is even lower than the probability of inverting, say, just the one-way function? Like even smaller than 1 over exponential. Does that answer your question?
So which implication will it go? Yeah, which implication will it go? So I mean, like the last hardness amplification thing. If you can show it, then you can. Sorry, I just want to make sure that I get the direction.
Yeah, if you can show the last implication, you still don't get much. But if you can show the last implication when replacing so the last conjecture, like one-way functions plus some random oracle amplifies, like hardness amplifies. If you can show that even when the random oracle is weakened by a collision finder, then you prove that one-way functions are black box useless for cohesion race and hash functions. But the first step will be to first prove the
You mean helpful? Yeah, Geoffroy, you mean helpful, yeah?
Yes.
Yeah.
Well, the first step will be to prove that one-way functions amplify in the presence of a random oracle without adding a collision finder there. And even this is open, but it looks like a very natural question.
So if you, hi, this is Salil. Just following on the same topic, if you don't kind of insist on focusing on this classic question of one-way functions versus collision-resistant hash functions, do you have any? Are there other? I mean, other examples that you know already, or would conjecture that might be easier to prove about something being black box helpful? I mean, you know, as you said, there are many examples in crypto where we use two different primitives to build some other primitive.
So black box. So so we have say artificial black box helpfulness, which are uninteresting. For example, the primitive public key encryption plus collision resistant hash function. Well, each of public key encryption and collision resistant hash functions are black box helpful for building it, but in isolation, each of them is black box separated. And you can work out this collision resistance plus public key encryption to get something that looks like meaningful cryptographic primitives, like IBE with some compact keys. So anything that will be some public key encryption, but you also want some kind of shrinking commitment to something. So very low rate public key encryption, some natural primitives like that, you can get essentially the same kind of black box helpfulness, like collision resistant hash function plus public key encryption imply each of them are helpful, but separately they are black box separated. That's
Great.
The kind of thing we
Thanks.
have.
Thanks.
And I'm curious, maybe on the opposite direction, because you mentioned that there are some black box useless. What would be maybe the most natural or surprising, or I don't know, I'm just curious. Well, I guess the conjecture, of course, for one-way functions from key agreement, but in terms of provable results, what is the most surprising black box useless result?
So in a way, the other we have are not surprising because they are built upon the compiling out paradigm. So there are many results in the literature that have been proven, black box separation that have been proven as follow. If you can build some primitive from another one in a black box way, then you can build it in the plain model. For example, that's the case for if you can have an efficient construction of a PRG from a one-way permutation. So that makes only not enough queries to the one-way permutation, then you have a PRG in the plain model. Well, what we show is that these results, they essentially relativize. So you get black box uselessness. So if you can build your PRG using some primitive plus a one-way function, and you do not make so many calls to the one-way permutation, then you don't need the one-way permutation in the first place. But in a sense, it's, say, not completely obvious. There are some technicalities related to showing that and proving exactly what we have. Mohammed could tell more about it because it's really related to many things in his works. So it's expected, but not completely obvious, but still expected in a certain sense.
But this is like efficiency separation, which is very interesting. So basically you're saying you cannot, if you want to have a very efficient construction, then, one-way functions are useless, I guess. But if it's not efficiency, if it's just feasibility, is something where, I don't know, you don't put efficiency restrictions?
Well, feasibility, there are a lot of results of that for I/O. Maybe
Yes.
a couple of weeks ago, I/O would be still kind of, in a different world. But I/O, if you consider it by now a standard primitive, like we know that many things cannot give you I/O with the same proof structure that Geoffroy explained. You basically compile them out from the I/O construction, and that compiling out process also relativizes. So that's a feasibility.
So for example, these all or nothing primitives, they are black box. So like witness encryption and the like, they are black box useless for building, say, approximate indistinguishability obfuscation.
Yeah. The catch is that it's not exactly I/O, it's like approximately correct I/O. Yes.
I see. So implication
questions for actually maybe just in case there's anybody else who has questions, otherwise you can keep going. All right, I guess you've got the floor.
I was just going to clarify, just so maybe, just very quick clarification for me. So interpretation of black box useless result means really, if I want to construct it, I shouldn't even consider this primitive at all. It's kind of something like strictly stronger. I'm just trying to see.
Not really. It might still help you in a non-black box way. Like one-way functions together with I/O give you public key cryptography. That's non-black box, but each of them alone in a black box way, they do not give you. So you should still kind of think about it, but in a non-black box way.
But yeah, so if you think about, you have a bunch of primitives and you would like to get a black box construction of another primitive, then you can exclude from your set all black box useless primitives. They won't help you in any black box construction.
So I had a question for one of the other speakers, for Mikito, if Mikito is still there. Yes. Hi. So just the question was whether there are any implications of your results or versions of them that relate to the complexity of zero knowledge proofs, because I mean that was the context in which these kind of AI primitives were first introduced by Ostrowski and Wigderson.
So sorry, I have.
So for example, if you want to base the hardness of zero knowledge on NP hardness, the non-triviality of zero knowledge on NP hardness, are there?
Yeah, to be honest, I have not considered about the point zero knowledge proofs. I just only consider the starting point is just NP hardness. So okay. I think it's a very interesting. So thank you. So.
Actually, I also have a question for you. What's your opinion? Are you optimistic or pessimistic in regard to lower, impossibility or new direction?
Yeah, I guess the very natural standing point is maybe negative at present because so the non-adaptive black box reaction for in the case of auxiliary input pseudo-random generator, then we can exclude the collapse of polynomial hierarchy. But then the existence of the auxiliary input pseudo-random generator and auxiliary input one function is equivalent. So very natural thought is even in the case of auxiliary input one function we can exclude. But in my opinion, the positive. So in the positive perspective, so the goal is very. How to say, very strong because we can get NP based one function. But that's why. So I believe the negative perspective, but I think we should not give up such a positive attitude at the first glance. That's why I consider the important direction is to verify the parity of positivity. Yeah, that's my opinion.
Nice. All right, any additional questions? Evgeny? He left. Okay, in that case,
maybe
then
just a comment.
thanks everyone for.
Maybe just a comment,
Yes.
right? I mean, like regarding all these, whether a one-way function can be constructed using a black box reduction from a worst-case hardness, right? I mean, there are some subtleties. I think a lot of people miss. There are some subtleties here that when you say black box, right? You really mean two things, which are not the same. One is the way the reduction accesses the primitive, right? So it queries and it gets answers back in a black box way. And the second thing is whether when you query the adversary, right, then are you assuming that this adversary is an efficient computation, or is the reduction supposed to work for every choice of adversary? And most of the separations that we have in the literature, right? I mean, when we say black box, we mean both, right? So what we mean is that you cannot do it with a reduction that queries the adversary in a black box way, and also it would work even if the adversary that is breaking the second primitive is inefficient, right? The reason I'm pointing this out is that there are results out there which are somewhat similar to what we want to prove, but weaker, right? The most famous one is probably by Hirahara from 2 years ago, but there's also an old result that we had with Gutfreund and Tashma, which basically show that, right, I mean, that you can somehow get, right, I mean, we do have reductions in the literature which are black box in the sense that they access the adversary in a black box way, but they are able to exploit the efficiency of the adversary. And for example, if you don't make this distinction, these results already break these black box separations. So the kind of results that we are proving using these techniques, right, are ruled out by these black box separations. So we should be very, right, I mean, we should be very careful when we say, right, I mean, things are impossible to prove in a black box way, but because we don't always mean the same thing, right? Like sometimes it can be bypassed by only slightly modifying what we mean.
So so in the paper, we really try to make the exact type of black box reductions extremely clear. Like we really say, if we have a black box reduction of this type initially, then we can compile out, say, the one-way functions and get a black box reduction of this type. And actually there is a loss. We get a weaker kind of black box reduction. And we also briefly discussed this notion of class reduction. I think this is what you're talking about. Yeah. So this notion that only works for efficient implementation of. So this we briefly discussed it actually in the context of black box helpfulness, because well, I was hiding a few things under the roof, but this notion turns actually to matter when we look at black box helpfulness of one-way functions for cohesion rates and hash functions. But yeah, we try to make the distinction very clear in the paper, and we also acknowledge like these class reductions as something to look at.
Yeah, so right, very interesting problem, right? I mean, like so far, right, with the exception of Hirahara, which is great, right? We've known these like class reductions for like almost 20 years, like 20 years now, and we haven't been able to do anything useful with them, right? I mean, somehow, right? I mean, we have this tool and we don't know what to do with it.
Yeah, I mean, we don't even have anything for separating one-way functions from key agreement for class reductions. So even like forgetting about black box uselessness and the like. So.
Right, any additional questions, comments, suggestions, future predictions? Okay. In that case, thanks to everyone for sticking around, for having the active discussion. I think this has been a lot of fun. And hope to see you guys around in the rest of the conference. And good to see folks.
And can I ask, is there a speaker from the last paper, the computational complexity of Heinlein-Zeckhauser? Is a presenter for that paper here? All right, we'll get started in a second. Can I ask quickly, is there a presenter for the computational complexity of the Heinlein-Zeckhauser scheme in the room? All right, I guess we'll work on that. But in the meantime, welcome to the next session. So if you want to ask questions, since we only have 4 talks instead of 5 in this session, I think it'll be okay if we do 1 question in between talks if you want to ask one. But we'll still try and finish by the same time as the other sessions and do the longer discussion with all the speakers after. You can also use the Q&A if you want to ask questions. I noticed there's a lot of co-authors of the papers here too. So if you want to ask questions in the Q&A, you can probably get answers during the talk, or the speaker can answer them after the talk too. So let's get started. So the first talk will be by Yiding Feng and is on batching and optimal multi-stage bipartite allocations. And Yiding, you can get started.
Okay, thank you, Matt. So today I'm happy to talk about my joint work with Red from Chicago. So this project is basically motivated by the real-world application in the online market, where the platform needs to dynamically match the demand request to the supply. And within all those applications, different applications have different allowance for the latency. In other words, the longest waiting time a demand request can wait before it has to be responded. And in the application which allows some of the latency, the platform can make the more efficient matching decision by using the batching strategy. Specifically, it will group the demand requests together in batches and then makes the stage-wise matching decision, one for each batch. It's easy to imagine that in this new paradigm where the platform using the batching strategy, the matching efficiency will be improved. So a question could be asked here is that, can we theoretically measure this efficiency improvement by using this batching strategy? And to do so, we need a theoretical model for this one. And before that, let's first revisit the classic model of online bipartite allocation. So in online bipartite allocation, there are different variation. For example, online bipartite matching, online bipartite packing, and some other variation. So in today's talk, we will mainly focus on the vertex weight B matching and say how can we modify it to capture our new paradigm where the platform can use the batching strategy. So in an instance of vertex weight B matching, it will be given as a bipartite graph, where on one side we'll have a supply node, which will be given in an offline fashion, where every supply node will have a heterogeneous weight, as well as a capacity, which captures the total number of demand requests it can be matched with. And on the other side, we'll have a demand node, which will arrive to the algorithm in an online fashion. And once the demand nodes arrive, the matching algorithm needs to make the matching decision for that node immediately. And in this talk, we will mainly focus on how to modify this model to capture in our new paradigm. And additionally, we will assume that the matching algorithm can produce the fractional solution. And we will assume that all capacity for the supply node will equals to 1. Cool. So far, the model assumes that the demand nodes will arrive one by one in an online fashion. And in our new paradigm, we will assume that they will arrive in batches. Specifically, suppose we are fixed that there will be k stage, and therefore a new batch of demand nodes will arrive in each stage. And for example, here is the instance of 2 stage, and therefore we'll have 2 batches. And another instance of 4 stage, and therefore we'll have 4 batches. And in our model, we do not have any assumption about so the number of demand nodes within each batch. Cool. Now let me formally define the class of matching algorithm we are considering. So once a batch arrives, the matching algorithm will observe the demand vertices within this batch, as well as the incident edges. And then this algorithm needs to make a irrevocable matching decision, which will be a fractional matching between those demand vertices and the supply nodes. And here the Yj corresponds to the current consumption of this supply node. In other words, it will be the fractional degree has been matched in the previous stage. And our goal is to maximizing the weight of the matching, and we are competing with an in hindsight solution. In other words, optimal offline. And in this paper, we'll try to identify the optimal competitive ratio if we fix the number of stage, capital K. And let me remind you that if capital K equals to 1, we will only have a single batch. So this will correspond to the fully offline problem. And therefore, we know gamma 1 will equals to 1. And in another extreme, where every batch contains a single demand vertices, this will correspond to the fully online problem. And in this paper, our formal research question is that in the middle ground region, where we have capital K batch, can we identify the optimal competitive ratio? And even though our model assumes that demand nodes arrive in batches, but we can always pretend that they are actually arrive in an online fashion. And therefore, the literature from the online bipartite allocation with vertex arrival tells us radial allocation will always be half competitive, and balanced algorithm will be 1 minus 1 over E competitive. And in this paper, we identify the optimal competitive if I fix the number of stage K. And let me remind you that this gamma K will be between 1 minus 1 over E and 1. For 2 stage, it will be 3 over 4. And for 3 stage, it will be 19 over 27. And as capital K goes to infinite, it will convert to 1 minus 1 over E. And we also show the same results hold for other variation of this model for both fractional solution and integral solution with large budget assumption. Now, let me give you some taste of our technique toward this result. So in this paper, we introduce the so-called polynomial regularized convex programming matching, and it will contain 3 steps. So in the first step, we will try to identify a sequence of polynomial with decreasing degrees, 1 for each batch. And once a batch arrives, we will try to write down a regularized max weight matching convex program, where in the objective function, we will use those polynomial we identify in the first step as a regularizer. And the solution of those convex program will be a fractional solution we assign at that stage. And at the end, to show that this algorithm attains the optimal competitive ratio, we will consider the KKT condition of those convex program. And those KKT condition will induce a graph decomposition, which we'll use to build up a primal dual analysis. And specifically, for the dual assignment we construct in those analysis, we'll be using the property of our graph decomposition. In other words, they will be inspired by the KKT condition of our convex program. And in this sense, the convex program we study in this paper provide a new interpretation for the classic primal dual analysis in the classic online bipartite allocation with vertex arrival. Specifically, for the dual assignment in those analyses, it can be solved as a consequence of the KKT condition of our convex program with some specific regularizer. And for example, for the balance algorithm, which attains 1-1/E approximation, its dual assignment can be solved as using our convex program. And instead of using the regularizer of using the polynomial, but using the exponential function as a regularizer. And that's all of my talk. So if you have any question, please feel free to ask question. And you can also connect me through my email. Thank you.
Thanks, Yiding. So we can take one quick question if someone has one while Clay, if you want to start sharing your screen. And if there's not one from the audience, Yiding, can I quickly ask? You mentioned that for the integral setting, you needed a large budget assumption. Do you believe that that's because you would need a more complicated algorithm to work with a budget of 1, or you believe that the algorithm, or you believe that there may be a stronger impossibility result? Yes,
I think this is a very good question. So first, the large budget assumption is the standard assumption for this kind of online matching literature. And on the other side, we also conjecture that the same competitive ratio can be achieved for the integral setting with capacity equals to 1. But certainly our current algorithm does not work, and we need to think about if there are some other ideas.
Cool. All right. Thank you very much. And we'll move on to the next speaker, who is Clayton Thomas, who will tell us about tiered random matching markets.
Thanks, Matt. And this is based on joint work with Atay Ashlagi, Mark Braverman, Amin Saberi, and Gong Zhao. So this is a paper about the stable matching problem. By a standard analogy, this is seeking to match n men to n women when each agent has preferences over all of the agents on the other side of the market. And our goal is stability, and this is the property that once I output this one-to-one matching, nobody wants to get up from their assigned partner and match with each other instead. This is used, heavily studied in theory and used in practice, and it's been argued to be really crucial to prevent market unraveling. I can tell agents when I give them this matching, why would you want to deviate from the matching? Nobody would want to do that with you. And it's used to match students to schools and residents to hospitals, as well as other things. The most common matching to use is the one-side optimal matching, which can always be found by the deferred acceptance or Gale-Shapley algorithm. As a reminder, this proceeds by the men proposing down their preference lists from their favorite to their least favorite, and the women tentatively accept the best proposal, reject all others, and they continue making these proposals. To study these markets, you kind of need to put distributions on the preferences of the agents. This really gives a lot of valuable insights that you'd miss by just doing deterministic studies. And to give us a baseline, one of these insights is that with n men, n women, and uniformly random complete preferences over the other side, the men are at a very large advantage. They get their log nth favorite woman in expectation, where women get much higher, much further down their lists and divided by log n. We call this place that the agents get the rank that they achieve. And a long line of work has extended this analysis and found a variety of different interesting models that show that different market parameters can have profound influences on these ranks, and that a lot of interesting things happen. But up until now, not much has been known, at least not in detail, for cases where the agents are non-uniform. Most of the tools were really specialized to this indistinguishable agents case. So in this work, we want to give agents some a priori quality before the market starts. There are some good and some bad agents that are less desirable. And what we'll be interested in is these rank statistics, how much agents like their matches, and we'll be interested in who ends up matched to who. So the distribution we study over preferences is a tiered matching market. This has a constant number of tiers for the men and for the women, with a constant fraction belonging to each tier. And there's these constant public scores, or you can think of it as the weight that the agents have attached to each tier. If this is a residence matching to hospitals example, maybe the tiers on the residents are the A students for medical school, the B students, etc. And the way preferences are drawn is from favorite to least favorite by sampling proportional to the score of the agents on the other side. So for one example, a woman W is the favorite of each man, with probability her score divided by the sum of all of the scores of the women. And for one more example, if W1 and W2 have score 9 and 1, then 90% of men will rank W1 above W2. We think this is a really natural next step beyond uniform markets. In fact, it's a special case of a pretty well-studied set of preferences called popularity preferences, which think of these scores as the popularity of the agents. The only additional structure we have is these tiers, big blocks of agents with the same score. But the key assumptions that the analysis uses are that the preferences are identically distributed for each man, and that these weights are constant. There's only constant variation in quality. Okay, so diving into the results. For the purposes of this talk, I'll phrase the results where only the women are in the tiers, and then when only the men are in tiers. So these expressions end up giving the rank that agents on both sides of the market end up achieving. The first thing we can notice is that up to constant factors, this matches the uniform setting. But the total number of proposals has increased by this factor, which depends on the smallest public score on the women's side, alpha min. This factor is the ratio of the average score, this dot product of the score fractions and the weights. And this is pretty natural because the bottom tier of women is a real bottleneck in this market. Men don't want to match there. And so they'll keep making proposals until finally that bottom tier is sort of matched. For women, the higher your score is, the lower your rank is. And this is in fact directly inversely proportional to the score. This makes sense. Better agents get better matches. And something really interesting to note is that the distribution or the tier proportions just factor out. They don't end up mattering for the women. They can sort of just think about their absolute quality above some baseline alpha min. When the men are organized into tiers, the ranks end up being given by this expression. These are all in expectation. And again, this matches the uniform market up to constants. And again, ranks are inversely proportional to score. But here, men have to worry about a little more. Their tier setup, the tier fractions delta, do factor into their type. And they sort of have to worry about the ratio of their score to the average, or more precisely, the ratio of their inverse score. Proving that these men's ranks is inversely proportional to their score ends up being like the technical crux of our paper. So just for some very brief intuition, the reason it comes out of the model is that it's sort of the case that increasing your score directly corresponds to increasing the probability that your proposals are accepted, and thus inversely corresponds to the number of proposals you need to make throughout the matching market. It turns out that when you put agents on both sides, these results still work together, and both men and women make a number of proposals which is proportional to their score. And this ends up having a really interesting consequence on what we call the distribution of match types. This is the expected fraction of matches in the output, which are between tier J of men and tier I of women. And we consider this for each I and each J. It ends up being the case that these fractions match what you would see from a uniformly random matching up to lower order terms. And this indicates that there's no sorting in this market. And instead, agents have to settle for things they idiosyncratically like and not things they like because of the tier structure. High types don't necessarily get high types. And just for a super short sketch of why this happens, in this market with just two equal sized tiers of scores 2 and 1, each woman receives twice as many proposals from the low tier men, but she weights the proposals from the high tier men twice as much. So in the end, it's 50-50 whether her favorite is from the high tier or the low tier. So for future directions, we would like to extend the model, say, to private scores instead of public scores. Things get a little more interesting when there are a lot more agents on one side. And we think a lot of these techniques or intuitions can be applied to mechanism design, but that's, of course, for future work. All right, thanks.
Thank you. So I think we fell a teeny bit behind time. So maybe can Hedja share your screen. And if you have questions for Clay, we have the long period after all the talks are done, or you can ask in the Q&A right now. All right. And the next talk will be on randomness and fairness in two-sided matchings, and it'll be given by Hedja Behaki.
Thanks, Matt. This is a joint work with Ava Tardush. So in this paper, we study matching markets where both sides of the matching have limitations. On the one side, we have the applicants that, although find a lot of the job positions on the other side desirable, they can only apply to a limited number of them. This may be because the system has imposed this limit or because preparing the applications is time-consuming and costly. On the other side, we have the job positions that need to run an interview process before hiring their applicants, and they can only interview a limited number of their applicants. Our goal in this paper is to study the effect of these limitations on the matching, and more particularly the size of the matching. Traditionally, the matching algorithms did not take these limitations into consideration. For example, the deferred acceptance algorithm by Gale and Shapley assumes that the participants can consider as many options as they want. In the more recent years, there have been more work on matching with limitations, but as you see, there's still very few studies on limitations on both sides. Let me define our model more formally. We have n applicants and n positions. We show the applicants by circles and the positions by squares. We focus on the case that the preferences come independently from uniform distribution that Clay also mentioned in his talk. So this simple case lets us make our analysis more tractable, and also we see interesting facts even in this simple case. We run a 3-stage matching mechanism. In the first stage, each applicant applies to k positions. Here, k equals 2, so each applicant is applying to 2 positions. Right next to each position, we show the applications they have received. In the second stage, the positions accept k prime of their applications for interview and reject the rest. Here, k prime is also equal to 2. The positions are accepting 2 of their applications and rejecting the rest immediately. After they run the interviews and refine their preferences, we run the applicant proposing deferred acceptance algorithm. And finally, we consider a large market setting, meaning that we study the market when k and k prime, the limits are constant, while n approaches infinity. And the main problem we focus on from here on is to find the expected size of the matching or fraction of matched participants as a function of k and k prime, the limit on the number of applications and interviews. Okay, so let's start with a case where the limit on the number of interviews is 1. We show that in this case, when n approaches infinity, the fraction of matched participants comes from this formula. The proof of this is not too complicated, but we won't get through that in this talk. Instead, I want to draw your attention to something more important, which is the shape of this function. Okay, so here on the x-axis, we have k, the number of applications, and the y-axis is the matching size or fraction of matched agents. So as you see with one application, around 63% of the participants are matched. It increases with 2 applications and 3 applications to around 68%. But after that, with more applications, the matching size decreases. And this is actually the first interesting fact that we observe in this case. So based on the formula, we know that the matching size is not monotone in the number of the applications. But intuitively, what is the main reason? We realize that having more applications has both a positive and a negative effect. The positive effect is that with more applications, the number of positions that receive any application increases. For example, with one application, only 63% of positions receive any applications. As you see, it goes up pretty quickly with more applications. But the negative effect is that since the applicants are applying to multiple applications, the probability that an accepted application belongs to some applicant who has other accepted application increases. So this leaves some of the agents with more than one offers, while the rest receive no offer. So in this picture, we see that after we increase the number of applications from 3, the negative effect takes over and we have a decreasing curve. Okay, so we completely understand what happens when the number of interviews is 1 and all the applicants are applying to the same number of positions. But is there any hope of achieving this larger matching if we allow applicants to apply to a different number of positions? So first, we show that given any average number of applications x, it is best to let a group of people apply to floor x number of positions and the rest apply to ceiling x. Basically, the largest size of matching happens when either all the applicants are applying to the same number or they apply to 2 consecutive numbers. Based on this lemma, we can find the size of the matching also in this case. Again, I won't go through the proof, but want to draw your attention to the shape of this new function that we have. All right. So on the x-axis, we have the average number of applications by each applicant. And on the y-axis, we have the size of the matching. And for example, if we are at point 1.5, it means that half of the applicants are applying to 1 position and the other half are applying to 2 positions. So here we see our second interesting fact, which is this U-shape between 2 integers, meaning that the local maxima of this figure happens when all the applicants are applying to the same number of positions. So I want to wrap up the case with a single interview with 2 messages. The first one is that the optimal number of applications is 3, no matter what distribution we choose to distribute the applications. And the second one is that a fair system of distribution gives the highest matching size, which means that the local maxima of the figure are the integer points. And more particularly, for example, if we are here, if everybody is applying to 2 positions, if we favor a group of people and let them apply to 1 more position, or if we discriminate against a group and let them apply to 1 less position, the size of the matching is going to decrease. Okay. I also want to quickly mention what happens when we have multiple number of interviews. So the formula and the solution for this case is going to be more complicated. But at the end of the day, we are able to find the expected matching size with arbitrary k number of applications and k prime number of positions. Here, the x-axis is again the average number of applications. And the y-axis is the size of the matching. Here we see the curve with a single interview that we saw previously. This is with 2 interviews, 3 interviews, and so on. So as you see with more applications, we still have our 2 weird properties, the non-monotonicity and also the U-shaped between integers as before, but it happens with a lesser degree. I also want to quickly emphasize that these weird behaviors are consequences of limiting the number of interviews. If we don't have any limit on the number of interviews, the matching size is going to be monotonically increasing in the number of applications. Okay, let me conclude. Our main technical contributions are 1, computing the expected size of the matching as the outcome of the deferred acceptance algorithm when there are limits on the number of applications and interviews. And 2, finding the optimal way of distributing the applications when we're given the total number of applications. Our work comes with 2 policy recommendations. The first one is that if we have limited ability granting interviews, we may need to limit the number of applications as well to have a large matching. And the second one is that the optimal matching size is achieved by a fair system. That's all. Thank you for your attention.
Awesome. Thanks. So I think let's go ahead with the last talk of the session, and then we can have the discussion afterwards. So I think that's
me.
Yes. Do you want to start sharing your slides?
Okay. Sorry. You see them?
No. It says you're screen sharing, but I just see a blank page.
This happened.
So this has happened a little bit. It might help if you, instead of sharing the application, just share your entire desktop.
No.
No? Well, clean it up and then give it a go.
Can you see it now?
Still no.
Okay. What happened here? Sorry.
So now we do see your desktop, I think.
Okay, can you see the slides now?
I don't think that's what we're looking at. I think we see a browser.
Can you switch to your slides?
Sorry?
Can you switch to your slides?
I have switched my screen is showing my slides.
So our view of your screen looks like it's showing a browser of a YouTube video.
Okay, that's this one. Okay, I'll cut it.
Yes.
I will just purge it, and I will start share screen and here this is what I want to share. Good, excellent. Now you should have it.
Now we see it.
Good. Okay. So welcome everybody to this talk, and I hope you can hear me. This is joint work with Mihalis Yannakakis, and what it is about is the computational complexity of this fabulous scheme of Hieland and Zeckhauser, 2 economists from Harvard. Actually, Zeckhauser was the advisor of Hieland, who was a student at Harvard. Zeckhauser is still at Harvard. Hieland is somewhere in Scandinavia. And Zeckhauser is a very important economist. Okay, and this is for one-sided matching market. So I know this is a very diverse crowd, so let me just say what a matching market is. So these are different from commodity markets in that, say for instance, college admission is a matching market. And the interesting thing to see here is that a student cannot buy admission to UC Irvine, no matter what she's willing to pay. She also needs to be chosen. That's talking about UC Irvine. At USC, some people have bought admission. Some rich and famous people bought admissions for their daughters, and then they had to go to jail. Okay, so so that's what this market is about. It's a market in which you cannot simply choose what you want. You also have to be chosen. And typically there's no exchange of money involved. So the big question is, why is this even a market as we know markets? And the reason that actually Al Roth gave me was that because it aggregates information held by the participants, which is what markets do. That's why these things are called markets. And by now there are lots of markets from all walks of life. And the best way I know how to classify them is through revolutions in computer science. The first one was, of course, the Gale-Shapley stable matching market, stable matching paper, which led to the matching of residents to hospitals. And in the so this is a very ancient field in that sense, matching students to schools, kidney exchange, and so on. And then what happened was these computer science revolutions of the internet, which gave rise to the AdWords market, which almost entirely funds Google's massive expenses, their free search, Gmail, YouTube, everything. Upwork, which matches workers to jobs. Mechanical Turk is similar. Match.com does the traditional matching of men and women. And then came mobile computing, which led to even more interesting matching markets. More interesting or not, but more matching markets, newer matching markets. Uber and Lyft, Airbnb. And there's one more matching market that's really relevant to all of us, which is not in this because it's not really mechanized like these ones. And that is the academic job market, where every hire is a one-off and you cannot really automate this process. Okay, so but that the fact that the job market has been a market in everybody's minds should tell you that this is not an anomaly to call it a market, these kinds of things. Okay, so this general and very powerful algorithmic tool. Okay, so here you can see that on the one hand, the field is ancient. On the other hand, it's in its infancy, because with these new revolutions, you certainly gave rise to very, very interesting, very, very impactful markets, which are occupying a bigger and bigger fraction of the economy. This is only a small sampling of these. So what we need really is these kinds of general tools, because if there's a new market tomorrow, you want to take one of these tools and off the shelf, just plug in a mechanism to start running it instead of devising yet another algorithm for it. And this goes back to 1979, Hieland and Zeckhauser, and they used the power of a pricing mechanism to run a one-sided matching market. Now, what's a pricing mechanism? Where you basically find prices through demand and supply, and that's you try to make a parity between demand and supply, and that gives rise to many, many nice properties. Has always been the central tenet in economics. It avoids artificial scarcity, has led to efficiency, has created massive wealth in the West, and so on and so forth. How exactly it comes about will be the next slide. But what's the one-sided matching market? So you saw two-sided matching markets in the last few talks. One-sided is where only one side has preferences, unlike say the boy-girl markets, where boys and girls both have, men and women both have preferences. So like agents and goods are dumb, they don't have preferences. Okay, and I just want to say that the Hieland-Zeckhauser scheme seems like a novelty in theory and theoretical computer science. In another theory, namely economic theory, it's a classic. So there's a new book coming out on matching markets. This Hieland-Zeckhauser will be in the very introductory chapter of that. So, so you can view this market as a marriage between linear Fisher market, which really is a market with money and goods, and goes about finding equilibria and is run through the pricing mechanism, and perfect matching. Okay, so think of the market as having n agents and n indivisible goods. And each agent has told us her utility for all the goods, uij for good j, that's for agent I. And we want to find a perfect matching of agents and goods so that the allocation is Pareto optimal, which means that the only way to improve any one agent's allocation is to diminish another one's agent allocation. So it's sort of maximally good. Yeah, of course, if you give, okay, yeah, there are trivial solutions to Pareto optimality, but it's also envy free and all that, so that you don't boil down to some trivial solution like. In this case, you cannot do that. But if you give all the goods to one agent, you'd say, "Oh, it's Pareto optimal." Of course, it's Pareto optimal. But that's not what we are looking for. Anyway, it's also incentive compatible in the large. So if you have lots of agents, no one person can cheat. And all these two properties really come about from the fact that we are running it through supply and demand like a pricing mechanism. And so let's talk about that. So in order to really be a Fisher market, goods have to become divisible, and that's done by making each good be 1 unit of probability shares. And you assume that each agent has $1 of money. This is fake money. It's no novelty today, but in 1979, this was a big concept to have fake money. And each good J has a price, non-negative, okay? And the allocation now will be 1 unit of probability shares to each agent, so that the entire allocation is a fractional perfect matching, because you will have at each buyer the Xij's adding up to exactly 1, at each good also the Xij's adding up to exactly 1. And these are fractions, these are probability shares. So each good is 1 unit of probability share, each buyer gets 1 unit of probability share. So you need to find such a fractional perfect matching through this pricing mechanism. And so going further, we define the notion of an equilibrium. So given prices P, so and an allocation. So always think of an allocation as a fractional perfect matching. So prices and allocation are an equilibrium if every agent gets a utility maximizing bundle of goods. So every agent solves this linear program subject to the fact, of course, that X is a fractional perfect matching. Okay, and one small point to be mentioned, which is what leads to Pareto optimality, is that, notice that an agent need not spend her entire dollar. She may be able to, her utility maximizing bundle may cost $0 for all we know. So that's what she'll get. But if there are several of these that cost less than $1 and are utility maximizing, then she should get the minimum cost. And only then we can prove that the entire allocation is Pareto optimal. This is a very subtle point, but very key to make sure that Pareto optimality holds for the entire allocation. And if you have worked on equilibria, you always have to put in the condition that the market clears, but that's guaranteed. If X is a fractional perfect matching, of course, all goods are sold, because every good is 1 unit of probability shares, and it's all sold by definition of fractional perfect matching. And once you get this fractional perfect matching, you apply Birkhoff-von Neumann theorem to round it up to an integral perfect matching, and that will also be Pareto optimal. That's very easy to see. Okay, and the point is, it is a very non-trivial, well, not very, but quite a non-trivial proof. There are more non-trivial proofs around this fact that equilibrium exists, and it uses the Kakutani fixed point theorem, which of course is highly non-constructive. So the question of efficient computability is front and center, and somehow it has not been addressed in our community. And the major hurdle here is that the market does not satisfy weak gross substitutability. What is that? That says that if you increase the price of one good, the demand of another good cannot come down. Okay, it should not. Normally, if you increase the price of one good, then other goods look better and their demand should only go up. Yeah, you have a question, Matt?
I was just giving you a heads up that time is out. So if you can try and wrap up in a minute or so, that would be good.
Lord, I haven't even started. Okay. So so you don't have, okay, so anyway, for the 0-1 case, we can give a polynomial time algorithm. It goes also for, okay, and here's an example with irrational equilibria, 4 agents, 4 goods. And the amazing thing is that this example satisfies all these equations, which would tell you that it's rational, because at each buyer, each good, and each agent spends exactly $1. How on earth are these irrationals adding up to ones everywhere? Okay, the consequences are it's not in PPAD, and we show that it's in fixed P by giving another proof of existence of equilibrium using Brouwer's 6-point theorem. And fixed P is much, much harder than PPAD probably. Of course, we have to show P not equal to NP to make that probably go away. And approximate equilibrium is in PPAD, where notion of approximation is appropriate to this proof. And the proof is to change the other proof a little bit. And how do you get hardness results? How do you efficiently compute equilibria, approximate equilibria? What do you do about 3-valued utilities? Because for 2-valued, it's rational and NP, 4-valued irrational, 3-valued we don't know. And there are many, many generalizations waiting to be handled, like 2-sided matching markets in this framework. But nobody wants to go anywhere near, because nothing can be even done about a 1-sided matching market. And if I have only 1 more second, then I'll just leave you with this very important number. Thank you.
All right, thank you. So we'll transition to the discussion part of the session now. So what we can start with is if anyone has any questions from the audience they'd like to ask to any of the speakers. I think someone can correct me if I'm wrong. I think it's okay if you're a panelist already and you want to just unmute yourself and ask that's okay. And maybe
if nobody has a question, I just want to ask somebody if they have guessed what 132 is.
I think we need your help.
That's the sum of the ages of the 2 authors.
Sorry, what's the
So it looks like there was someone in the audience who raised their hand. I think I didn't. It looked. Let me see. I think you can talk now.
Yep. Can you hear me?
Yes.
Cool. So I had a query with respect to the last author's presentation. So what's the empirical evidence that you have supporting your complexity? I mean, because it's one-sided matching markets. So I was thinking more in terms of the implementational, the empirical implementation, and what was the data structures that you used, if any, to.
No, we don't know that it's hard yet. No, we haven't proven hardness results.
Okay.
It just okay. I don't know. I don't want to take a crack at that kind of a question without solid evidence. But we really, I mean, all these years went into trying that.
Okay. Yeah, because the theoretical bounds look good, but yeah, empirically.
No, there's no theoretical bound. We're just saying that it's fixed. It lies in fixed P, and fixed P is fixed P complete problems are likely to be very close to P space complete problems, not close to P. So the theoretical results are not pointing to anything very useful here.
Yeah. Okay.
The only
Got it.
theoretical
Thanks.
result pointing to useful is when you have 0-1 utilities and extended to when everybody's utilities are 2-valued, bi-valued. Everybody has 2 numbers, and all the utilities come from those 2 numbers, but the 2 numbers can be different for different agents.
Thanks.
And as soon as we have 3 numbers, we raise our hands and we are we cannot say anything about it. For 4 numbers, we have irrational example, and that's the reason that the problem is not even in PPAD, because every problem in PPAD has to have rational solutions. And this example has only an irrational solution and no rational solutions, even though all those equations that I showed you must hold for, or do hold, even in fact, even for that irrational solution.
Thanks. Vijay, can you also turn off your screen share for the rest of the discussion?
Oh, good. I thought everybody wanted to stare at the number a bit more. Okay.
So I have a few questions, but people in the audience should feel free to interrupt me with questions of their own too. So can I get back to Clay? So in your model, you said that all the results held when each tier constituted a fixed fraction of the market. And I'm wondering how sensitive the results are to that assumption, or if some sense of them would hold if everyone had an individual score, or what would you expect those results to look like instead?
So in that respect, the tiers are mostly for like cleanness and convenience. The key results that it's proportional to your public score would actually still hold. But we couldn't write down what those ranks would actually be.
Got it. Thanks. And then I had a question for Hedya too. So at the end of your talk, you mentioned some policy implications for the work. And I was just wondering, this may be an open-ended question, but I guess sort of like how literally would you take those recommendations? Or if you wouldn't take them super literally, what's the next step that you would want to see in this line of research?
Right. So the assumption that the distributions come from uniform distribution is essential for our results, but it's mainly essential because of the technical reasons. So like we can only calculate our findings when the distributions are uniform. So it depends on how much still the same weird behaviors hold with non-uniform distributions. So I think like maybe that's the first step to make the model more realistic. But I just want to mention that we kind of understand study the role of the randomness. And there are other papers that study kind of the extreme case when the preferences are almost identical or very correlated. So in that case, the congestion is mainly like the non-monotonicity, or the congestion is mainly because of popular agents. And here we get the opposite case. So it depends on how much, when we look at the models in between, the things hold.
So wait, sorry. Are you saying like the findings reverse in the really correlated model?
If you get the congestion, it's mainly because, for example, let's say that some people are much more popular than the rest.
Yeah.
So they will get like a lot of offers, right? So like in that case, it's not too surprising to see that with more applications, your matching site may decrease.
Right.
And then I have maybe one follow-up question that's maybe appropriate for either Hedya or Clay. So I guess Clay's paper involved a model that was kind of like barely beyond uniform. Do you have any sense of, if someone were to push in a next direction, if you were to pick maybe one side of the market to be drawn from a model more like the one from Clay's paper, is your intuition that that still immediately becomes intractable? Or do you think there's hope of that maybe being a good direction, and which side of the market?
That sounds like a great direction to me, because it's, as also Clay mentioned, it's maybe the first step to go beyond uniform distribution. I should think more of like which side of the market to be tiered. Maybe Clay has some ideas.
For our paper, putting the proposing side in tiers was much harder, but it might depend on the exact model. The fact that the like non-sorting fact that we got, we sort of interpreted it that you need something stronger or different than our model to, for example, tell people who they should interview. since the real stable matching in our model doesn't tell you who should match to who with any significant predictive power. Maybe you would need something like polynomial gaps in scores.
All right, and I think there's one more paper-specific question from Aviad that's written down, so I'll just read it out loud. Is Vijay, can you elaborate on what you meant by an extension to two-sided matching?
Oh, yeah. So suppose that you have two sides. So these are not agents and goods being done, but let's say agents and employers. Okay, workers and employers, and each side has preferences for the other side, given not through a preference list like in Gale-Shapley, but given through utilities, UIJs and WIJs. Okay, and now you can extend the definitions to get a notion of equilibrium and so on and so forth. Does it exist? What are algorithmic results there? What are irrationality results there, more importantly, because those will be many, many more. Probably, my guess is even 0, 1 is irrational. So I played around with it quite a bit without getting any positive results. And there are, so I've been in touch with Zeckhauser, and the very first time I sent him an email, he sent me this long a list of models that he wanted to attack. And I told him, look, we cannot even do the basic model. How can we go any further? So, so the point is that you can think of many interesting models. And he said, this is interesting, and this is interesting, and this is interesting. Yeah, they are interesting, but what can we do? So we are waiting really for some positive news on maybe approximate equilibria or something else before we can head to all those models. And I think the economists and maybe even the applications, people will like them once they get found and worked out. But good question, Aviad. Let's do it next fall together.
Do you think approximation is doable? Or should that be hard?
I have really tried hard. The weak gross substitutability, which is the main stumbling block for exact computation, comes up very strongly in approximate also. Sometimes one can get around weak cross substitutability. People have some results like that, but in this case, it's quite severe. I have some other ideas. Maybe if they pan out by February, March, I will share them with you through some forum or the other.
Thank you.
Cool.
But please be mindful of the age of the authors, because the younger people have to take over the mantle now.
Cool. I just want to give a quick heads up to everyone that it's almost to 11:30, and the next session is going to start in room B. There's still another question, so we'll take the question and we'll keep talking. But if you were hoping to go to the next session, that was just this is your warning that it's going to start soon.
Okay.
So there was a question for Clay in the chat. I'll just read it out loud for the recording. Do you have any thought about how to check empirically your result that every pair of agents has the same probability of being matched property?
So we've checked it with simulations, or rather Gung has checked it with some great simulations. And although the convergence is really slow, it does go to uniform in constant tiers. In real life, I don't know if we could find markets that satisfy these assumptions really well. Preferences are really correlated. Even if the gap is pretty big between, say, Harvard and Cambridge Community College, a constant score gap would predict that 1% of people would rank the community college above Harvard. So I would say that this points in the direction that this indicates that you need stronger assumptions to get the sorting that we see in real world markets.
Nice. So I had only prepared kind of like one more general question myself, so I'll just ask, but speakers, you should feel free to just ignore it and drop off if you're done. So I was curious if the speakers or any of the co-authors who are panelists who wanted to share, if you wanted to share, maybe is more relevant for the students in the audience, what was like the most exciting paper in the research area relevant to what you just presented that kind of like got you really hyped to work in this area, or that got you excited to start whatever project you just presented? Or it could be a series of papers or something. And I guess we can go in any order, and the co-authors who are visible can share too.
So for me, I think it was actually, Matt, when you told me about the Ashilagi-Kanoria-Leshno result, that with just say N men and N-1 women, the advantage of being the proposing side is basically completely neutralized. And it's better to be a woman because you just have that one fewer agent, and imbalance is really powerful.
So maybe I can go next. So for this literature of online matching, so I think the most inspired paper for me is a KVV's paper in 90s, which introduced this very fundamental model. And so later in the DJK13 paper, they introduced this classic framework of primal dual analysis to analyze this competitive ratio. And even in the recent study for more complicated model, they are also try to adapt this primal dual analysis. And I think those are all very great paper.
Can I add a comment to your thoughts?
Yes.
So following up on the primal dual analysis, there was exactly based on that, really taking all their ideas. There was a paper of Michael Feldman and Amos Fiat and some other people giving an economics-based analysis, and that's particularly clean. And these two are really, for the first time, textbook quality analysis, because KVV was never in a textbook. And as I mentioned, there's a book on matching markets. In one of the fundamental results chapter, there'll be an exposition of KVV. It'll be on my website as soon as I put it there, that chapter. And you can see the very, very, very clean analysis, so beautiful, coming from these two papers. It's finally, you can teach it, I believe, even to undergrads, certainly to graduate students. I'll put it on my webpage. I promise. Today is what, Wednesday? Certainly by next Monday, you will see it on my webpage.
Nice. And for those of you following in the chat, there's also some references to the papers that just got mentioned.
Yeah, talk at SOSA this week. Yeah, that's Kira just mentioned that the Michael Feldman et al. Paper will be in SOSA. Yeah, Alon Eden also, yes. And I believe Amos Fiat, and maybe there's one more author. I forget. Yeah, cannot remember everything anymore.
All right, I guess if no one else wants to share, we can end the session. I guess, Hedja, do you have anything you want to share?
Sure. For me, it was a Morlika Mahdian paper from 2005 that got me interested in this whole matching market with shortlist, and they're actually like interesting solutions. That's quite interesting for me.
Nice. Okay. So maybe we can end the session, but I think a lot of the authors mentioned that they're happy to follow up offline, and we'll see you all back in Gather. Thanks for joining.
Luca, do you want me to share your screen, or do you plan to say something at the beginning?
Well, feel free to go ahead and share your screen. Meanwhile, I just wanted to welcome everybody back to this afternoon or evening session. This topic will be pseudo-randomness and lower bounds. I would like to ask all the speakers to make sure to stay within their allotted 8 minutes. And also, I would like to ask the audience if they have a quick question to ask it at the end of the talk. If they have a question that probably is going to have a longer answer, maybe hold it until the end of the session where we're going to have time for a longer discussion. So we start the session with a talk on sum of square lower bounds using high dimensional expanders, and Madhur is going to give the talk. Please.
Can you hear me okay? Hi. Welcome everyone to the virtual talk, and I'll be talking about some connections between sum of squares hierarchy and certain pseudo-random objects called high-dimensional expanders. This is joint work with Irit Dinur, Yuval Filmus, and Prahlad Harsha. So high-dimensional expanders are just notions of expanding hypergraphs. There are actually quite a few different definitions of what it means to be an expander hypergraph, motivated by combinatorial, spectral, and topological considerations. We won't go into the precise definitions during the talk, except I should say that there are explicit constructions given by Lubotsky, Samuels, and Vishnay of objects which satisfy many of these definitions, and then these are the ones that we will use here. And although this is a new area, high-dimensional expanders have already found a huge number of applications to many different areas in theoretical computer science. And today I'm in particular going to talk about their application to constructing hard instances for certain optimization problems. The specific optimization problem I'll be interested in is 3XOR, which is just a system of linear equations over F2. So suppose you are given a system of m linear equations in n variables, each equation having 3 variables over F2. And the goal is to find an assignment to the variables satisfying as many constraints as possible. And we can also think of it as being an instance being specified by a collection of 3 tuples script t, which form the left-hand side of all the equations, and a function beta from this collection script t to f2 or 0, 1, which forms the right-hand side of all these equations. So the instance is specified by a collection of left-hand sides and a collection of right-hand sides. The optimization algorithm we will consider for this is something called the sum of squares hierarchy, which is actually a family of algorithms. It gives semi-definite programming relaxations for combinatorial and even continuous optimization problems. It can be thought of as a computational model, in particular for constraint satisfaction problems. If you think of the hierarchy comes in levels, and if you think of the tth level, it can be solved in time and to the order t. The specific relaxation will not be as relevant during the talk, but just in case you want to see, this is a relaxation for 3XOR given by the sum of squares hierarchy. The thing I would like to note is it's parameterized by this parameter t, and then there is a unit vector for every subset of the variables of size at most t, and this is what defines the hierarchies. And you can think of it as kind of an algorithm which does all kinds of local reasoning up to a locality of size t, but it also does spectral things. And one aspect that I want to focus on is that there are many known kind of lower bounds for this family of algorithms or this computation model, also many upper bounds, but the lower bounds in particular rely on random instances in one way or another. I mean, either you have a random instance or you start from random instance, do some reduction on top of it, etc. And our goal is to construct explicit instances. And in particular, the result I want to compare against is it's known that if you look at a random 3 XOR formula, choose the left-hand sides and right-hand sides both at random, sufficient number of constraints, then the instance is not satisfiable, and in fact is far from satisfiable. No assignment satisfies more than 51% of the constraints. On the other hand, the SOS hierarchy thinks it's completely satisfiable and fails to even refute it, which means just prove that there can be an assignment which can satisfy all constraints as far as the SOS hierarchy is concerned. And in our work, we kind of give an instance which is constructible in deterministic polynomial time, but is weaker in certain senses. So first, these instances, if you think of this number mu as say 0.1, then what we essentially say is that there are instances which no assignment satisfies more than 90% of the constraints. And SOS still fails to refute it, so the SOS hierarchy still thinks that the instance is completely satisfiable. But for known random instances, this can be proved even for linear number of levels or omega n levels of SOS hierarchy. Here we can only prove it for square root log n levels. A couple of comments about the result. So to some extent, this issue of 1 minus mu or 90% versus 51% can be sort of handled, in particular combining with known reductions and inside the SOS hierarchy. One can show that there are explicit instances in which the soundness is half plus epsilon, so no assignment satisfies more than half plus epsilon fraction. SOS thinks almost all constraints are satisfiable or 1 minus delta, though not quite 1. And you can also obtain gaps or explicit instances for many other problems using reductions. To the best of our knowledge, this is the first explicit integrality gap construction. I should say that if you are just interested in distinction between satisfiable and unsatisfiable, there are things called Scythian tautologies, which are essentially systems of XOR equations, which is an unsatisfiable system. SOS thinks it's satisfiable. The construction is explicit, but there is no gap. It's kind of almost satisfiable. If you just kind of delete one equation, the system becomes satisfiable and don't quite have a gap between soundness and completeness. Another interesting thing is, I mean, the instances are not just explicit, they have a nice structure. In particular, they're based on these high-dimensional expanders, and in this sense, they offer maybe a subtle contrast or even a maybe apparent contradiction to known algorithmic results. In particular, it's known that for 3 XOR instances on high-dimensional expanders, constant number of levels of SOS can obtain an arbitrarily good 1 plus epsilon approximation. And here I'm telling you that 3 XOR instances, again, on high-dimensional expanders that are hard for square root log n levels of SOS. I mean, to the best of my knowledge, both these results are correct. It's a different definition of on, or what it means for an instance to be on a high-dimensional expander. And let me just illustrate this a little bit, and also to give the construction. So just to do this, think of a hypergraph as like we'll think of a simplicial complex, which is just a fancy word for a downward closed hypergraph. So we'll think of collections of 3 tuples, 2 tuples, 1 tuples, and sort of subsets of any 3 tuple are also contained, and we'll just call them edges, vertices, and triangles. And if you think of a 3 XOR instance with the variables corresponding to the vertices of a triangle and constraints corresponding to triangles, and if you have such a structure sitting on a high-dimensional expander, then it's known to be easy if your high-dimensional expander is a good one. On the other hand, the instance we construct, a triangle also has 3 vertices and 3 edges. So if you think of your variables as sitting on the edges of each triangle in kind of a 3 uniform hypergraph, let's say, and if this is a specific simplicial complex or expanding hypergraph, in particular the Ramanujan complex by Lubotsky, Samuels, and Vishne, then we can show that the instance is actually hard. Okay, and I won't go into the proof here too much, except to say that in proof complexity, such things use kind of expansion of the formula, and here they are replaced by some sort of topological expansion properties of these complexes. In terms of open questions, it's kind of a subtle contrast between these vertex or edge variable constructions. It would be good to understand it more. we kind of stop at square root log n, but it's not clear if that's necessary, and other applications would be good to find. Okay.
Thank you, Madhur. So I'll ask the next speaker to start setup, and meanwhile, if there is any quick question for Madhur, we have time for that.
Salim has a question.
Hi, yeah, Madhur. I may be misremembering, but I vaguely recall this sort of distinction between putting the variables on edges versus vertices. Maybe came up in the context of coding and kind of expander codes versus LDPC codes. Is there any connection there to kind of what's happening in what you're doing, or just superficial similarity?
I mean, okay, I can give a slightly longer speculative answer, so maybe we can talk about it after the session. But
yeah, let's do that.
Okay.
Okay. That sounds like a question that deserves a longer answer. Okay, so for now, thanks, Madhur. And our next speaker will tell us about lower bounds for Turing machines derived from multiplayer parallel repetition.
Hello, everyone. So
Hi, Kunal,
I'm going to be, can you hear me?
Yes, we do.
Okay, so hi, everyone. I'm going to be talking about block rigidity, multiplayer parallel repetition, and lower bound for Turing machines. This is joint work with Ran Raz at Princeton University. So our main result is the following. We show that a strong multiplayer parallel repetition theorem will imply the existence of something we call explicit block rigid functions, which will further imply superlinear lower bounds for Turing machines with advice. First, I'll start by talking about Turing machines. Turing machines are the standard model of computation used to define complexity classes. Lower bounds for Turing machines have been long known via the time hierarchy theorem. Paul Peppenger, Semeredy, and Trotter also showed a separation between non-deterministic and deterministic linear time for multi-tape Turing machines, but no such results are known in the non-uniform setting. The model we are interested in is the following. We'll consider deterministic multi-tape Turing machines that compute multi-output functions. So what I mean by that is that we'll assume that the Turing machines have separate input and output tapes. And at the end of computation, the machine will write the entire output on the output tape and then halt. We'll also allow the machines to be non-uniform. That means that the machines are allowed an advice string, which is a function of only the input length and is written on a separate advice tape at the beginning of computation. Our main result is the following. Let t be any function that is superlinear. Then assuming what we call the main conjecture, there exists a function f such that f maps n-bit inputs to outputs that are of at most n bits. The function f is computable by deterministic multi-tape Turing machines in time t, but the function f is not computable by any multi-tape deterministic Turing machine in linear time, and that takes advice. Next, I'll talk about block rigidity and what our main conjecture is. So in my opinion, the definition of block rigidity is like the main technical contribution of this paper. We'll be considering functions that take n times k bits as inputs and that output n times k bits. We say that such a function is r comma s block rigid if the following holds. So what we want to say that it is not possible to find a large set of inputs x of 0, 1 to the nk, over which each output block of the function can be written as a function of a small number of blocks of input variables. So the formal definition is the following. We require that for every subset x of inputs of size at least 2 to the nk minus r, and suppose we define subsets s1 to sk of 1 to k. So basically these will index the blocks which will be used to write the output blocks as functions of the input blocks. So we want these subsets to be of size at most s and functions g1 to gk. So the ith bit ith function gi will take as input the blocks of the input that are indexed by si, And we require that GI outputs the ith block of output of f of x. And we want to say that for any large enough set, this is not possible if f is r comma s rigid. In the case n is equal to 1, we'll call such functions r comma s rigid functions and not block rigid. So the word rigid comes from relation to Valiant's notion of rigid matrices. More details about this are in the long talk. So I'd say one thing, the notion of rigid matrices was introduced by Valiant to show lower bounds against logarithmic depth and linear size arithmetic circuits. The notion of rigid functions, which corresponds to the case n is equal to 1, corresponds. So essentially, the same proof gives lower bounds against general Boolean circuits. For our lower bounds, we'll mostly be interested in the case when k is just slightly super constant and r comma s are omega of nk and omega of k. So this corresponds to very strong block rigidity. The main conjecture is the following. So suppose f, which takes in k bits as input and k bits of output, and which is an omega k comma omega k rigid function. So or more strongly, suppose f is a random function. So random functions satisfy such a property with very high probability. Then we conjecture that the function f to the n, which is from 0, 1 to the nk to 0, 1 to the nk, is an omega of nk comma omega of k block rigid function, which is the domain we were interested in. So what is the function f to the n? So basically, the idea is to think of the input as a k cross n matrix, and we just want to apply f to each of the columns, which is of size k, and then the new matrix is the output. I would like to mention the connection between this and multiplier parallel repetition. If you do not know what multiplier parallel repetition is, I would recommend you to watch the longer talk. So I'll just state the results here. So we show that a strong parallel repetition theorem for a certain class of multiplayer games implies the main conjecture. Our class of multiplayer games satisfy a very special property, which is the following. For every random string of the verifier, there is a unique correct answer for each of the players. So we refer to such games as independent games. We believe that this strong condition may allow us to prove very strong parallel repetition on such class of games, despite very less known bounds on multiplayer parallel repetition. At the end, I would like to mention some other directions. The first is, can we prove strong block rigidity for other functions? This would imply superlinear lower bounds against Turing machines with advice for those functions. Some candidates are the following. The first is matrix transpose. So given an n cross n matrix A in row major order, we want to output its transpose in row major order. This is basically a problem on permuting the input in a certain form. The second problem is matrix product. So given two n cross n matrices A and B, we want to output the product matrix A times B. Block rigidity for these functions translates to answering very simple combinatorial problems. I would like to mention the problem for matrix transpose here. It basically translates to the following combinatorial question. What is the size of a largest family of n cross n matrices that satisfies the following? What we want is that in this family, for every matrix in this family, the columns of the matrices can be written as a function of a small number of rows of the matrices. So formally, we want to find subsets S1 to Sn of the rows, each of size n over 100. This n over 100 can be replaced by any small constant times n. And functions g1 to gn, which take in these rows indexed by S1 to Sn, and they output the jth column. So the formal definition is stated here. We conjecture that the size of such a largest family is at most, or the density of such a largest family is at most 2 to the minus omega of n square. This would imply that the matrix transpose problem cannot be computed by multi-tape deterministic Turing machines that take advice. So I'll end with this open problem. Thank you.
Thank you very much, Kunal. Is there any quick question for Kunal about his talk?
I might be missing something, but right, so strong parallel repetition does not hold for two-player games. So why are you hopeful that it would work for multi?
Yeah. So, but the class of games we described, so I said they satisfy this very special property. So we believe that the class of games that satisfy this very special property, it might be possible to prove strong parallel repetition.
I see. And do you know if it works for two-player games, like for this subclass of?
Okay, so the thing is that if we have games that have k players, the kind of bound we want on the nth parallel repetition is something like 2 to the minus k times n, some constant times k times n. And the class we are looking at, it is very easy to prove bounds like 2 to the minus omega of n. So the question itself becomes interesting when the number of players is also growing with n.
I see. Thank you.
Thanks again, Kunal. So I'll ask the next speaker to set up for their talk.
Sure.
Which will be on pseudorandom generators for unbundled with permutation branching programs. Go ahead, William.
Thanks. Yeah, so I'm presenting joint work with Ted Pine and Salil Vadan about pseudorandom generators. A pseudorandom generator is a function that stretches a short, truly random seed out to a long pseudorandom string. And the way we make this precise is we consider some class of test functions, f. And the requirement is that for every function in this class, if you look at the acceptance probability of f on a pseudorandom input versus the acceptance probability of f on a truly random input, those two acceptance probabilities should be within epsilon of each other. So epsilon is the error of the pseudorandom generator. And the test functions that we're going to be looking at are based on ordered branching programs. So this is a simple model of computation where we have some directed layered graph. So there are n+1 layers of vertices, and each vertex has two outgoing edges pointing at the next layer of vertices, and the two outgoing edges are labeled 0 and 1. A program like this can read an input string as follows. You start at the designated start vertex in the first layer, and then you read the input string from left to right one bit at a time to decide which outgoing edges to take from each vertex. So in this way, you walk through this directed graph and arrive at some vertex in the final layer. There's one vertex in the final layer that's the designated accept vertex of the program, and the program accepts or rejects the input depending on whether it arrives at that accept vertex. So in this way, a program like this computes some Boolean function f on n bits. One of the most important parameters of a branching program like this is the width of the program, which is the number of vertices per layer. The width measures the space complexity of this computational process. The most important case is width n, length n ordered branching programs, when the width is equal to the length. There's a simple argument based on the probabilistic method that shows that there exists a pseudorandom generator for width n, length n ordered branching programs with seed length log n over epsilon. And we would really like to design explicit pseudorandom generators with the same seed length. That would have some nice consequences, one of which would be this de-randomization result. It would imply L equals BPL, so the de-randomization of space-bounded computation. Unfortunately, so far, the best explicit constructions are not as good as the best, as what the probabilistic method gives. In fact, the best explicit pseudorandom generator for width n, length n ordered branching programs is Nissan pseudorandom generator from 30 years ago, which has seed length like log squared n plus log n times log 1 over epsilon. And so because it's been so long, there have been so many decades without improvements on Nissan's generator for the general case, researchers have looked at more restricted classes of branching programs to try to make progress. One example of this of a more restricted class is what are called permutation branching programs. So this is where we add this extra assumption that says in each layer, if you look at just the edges labeled 0, they form a matching. And if you look at just the edges labeled 1, they also form a matching, or in other words, a permutation on the states, a permutation on these states of the branching program. So this condition means that we're considering some notion of like reversible computation, like you can recover, you can run the computation backward. And in particular, it implies that the program is regular, meaning that each vertex has 2 incoming edges. And so there's been a lot of research on explicit pseudorandom generators for permutation branching programs and for regular branching programs. And at this point, we do have explicit pseudorandom generators for constant width permutation branching programs with a better seed length log n times log 1 over epsilon. Unfortunately, though, for the larger width case, like the most important case, the width n case, prior to our work, the best pseudorandom generator was still Nissan's pseudorandom generator, even for permutation branching programs. So that's where we come in. We were looking at wider permutation branching programs, and we actually said, let's go ahead and skip past polynomial width and let's go all the way to unbounded width. So at this point, when we're talking about unbounded width branching programs, this is no longer about the de-randomization of space-bounded computation, because we don't have a bound on space anymore. Instead, it's like de-randomization of some model of reversible computation, this permutation condition. So what we prove, our theorem says that there is an explicit pseudorandom generator for unbounded width permutation branching programs with seed length roughly log n times log 1 over epsilon. So it's roughly the same seed length that was previously known for the constant width case. And here we have this seed length with absolutely no dependence on width whatsoever. The pseudorandom generator itself is not new. It's the INW generator, for those of you who know what that is, Impaliazzo Nissan Wigderson generator. So it's the same construction as ever, but it's a different analysis. There is one crucial assumption that I really want to highlight, which is that in our model of permutation branching program, we only allow a single vertex in the final layer to be the designated accepting vertex. It maybe sounds, in some cases that's sort of a technicality, but in this case it really makes all the difference. And this is a crucial assumption. It's a big caveat. So the only previous result about this sort of strange unconventional model was by Day, who gave a seed length bound of log squared n plus log n times log 1 over epsilon. So it's like the same as Nissan's generator for the polynomial width case, but Day showed it for the unbounded width case. So to prove our theorem, some of the concepts that we use are the concept of the de-randomized square by Rosenman and Vadon, and then this recent notion of unit circle approximation, which was introduced at Fox this past year by Ahmadinejad, Kellner, Murtaugh, Peebles, Sidford, and Vadon. And we really rely very heavily on their results and their analysis of this unit circle approximation. So for context, let me tell those of you who maybe don't work on pseudorandom generators, tell you a little bit about how these sorts of problems usually go. What we're used to in the pseudorandom generators world is we're trying to design pseudorandom generators for some class, and first we can just do a simple probabilistic method argument to show that there exists some pseudorandom generator with a great seed length, maybe log n over epsilon. And typically it's really easy to prove a matching lower bound, show that that's the optimal seed length. And so the main challenge in the usual case, the main challenge is to devise an explicit construction that matches this probabilistic argument. But the model that we're studying, this unbounded width permutation branching program model, is a bit strange and unconventional. And this whole story provably breaks down. So let me explain what I mean. So you could consider sampling some generator uniformly at random from all functions mapping s bits to n bits. And then we prove that unless the seed length is really high, like close to n, with high probability, G fails to be a pseudorandom generator for unbounded width permutation branching programs. Okay, so this is a case where an explicit construction, the INW pseudorandom generator under our analysis, is much, much, much better than a randomly chosen generator. Right, the randomly chosen generator would need near linear seed length. The proof of this is pretty elementary. The main step is just identifying a suitable hard family of functions that can be computed by exponential permutation branching programs. So because the probabilistic method fails to guide us, it's not a reliable guide for this model in telling us about pseudorandom generators. This sort of calls into question, what is the optimal seed length for this model. And it turns out we proved that any pseudorandom generator for unbounded width permutation branching programs must have seed length at least roughly log n times log 1 over epsilon. So this lower bound basically matches our upper bound regarding the INW generator. And so it means that in this setting, the setting of unbounded width branching programs, permutation branching programs, the INW generator is near optimal. And so this is strange. It's different than what we're used to. Usually for pseudorandom generators problems, what we expect is that the optimal seed length should be something plus log 1 over epsilon. But this is a strange case where the optimal seed length is log n times log 1 over epsilon. So some of the tools we use to prove this are some tools from matching theory and some tools from information theory. Okay, so just to conclude, we studied this unconventional model of permutation branching programs with no bound whatsoever on the width of the program, and I think that this model pushes back against some of the standard intuitions that we're used to when it comes to pseudorandomness and derandomization. For that reason, I would suggest that it might be useful to have this model and these results in the back of your head as potentially counterexamples, to any conjectures you might start formulating about pseudorandom generators. And there are some open questions. We give several in the paper that are about like extending this work to even more general cases, and I'd be happy to talk about them. Thanks for listening.
Thank you, William. So actually, William's talk ran a little bit late, so I suggest to skip directly to the next talk. So even if you have short questions for William, hold them until then. William, please stop sharing the screen so the next speaker can share the screen. And next talks will be on notions of pseudo-entropy for very limited classes of statistical tests and whether they are equivalent or not. And the speaker, I guess, is going to be Sam.
Yeah, can you hear me all right?
Yes, go ahead, Sam.
Okay, great. Yeah, so thanks for the opportunity to share this. My name's Sam, and this is based off of joint work with my advisor, Russell. And yeah, so I'll talk about so different notions of computational entropy as well as the dense model theorem. Okay. So the starting point for this project is a statement called the dense model theorem. And this is a result in pseudorandomness with applications and kind of a surprising diversity of areas. So the first application was in additive number theory. And this was due to Greentow and Tao Ziegler. And they were interested in using it to solve a number theory problem. They wanted to find arithmetic progressions in the prime numbers. And they used this, to prove the Green-Tao theorem, which is, kind of a landmark of the past 20 years in mathematics. Another interesting application, which doesn't have anything to do with number theory, is in differential privacy. So Mironov et al., they were able to use the dense model theorem to give relationships between different computational definitions of differential privacy. Okay, so let's work kind of towards stating the theorem. So we basically start with a set S over a finite universe U, and we think of the set as being small. Okay, and the dense model theorem will give us basically sufficient conditions for S to look like it's dense according to some class of tests. Okay, and the test class will consist of functions which are kind of which have bounded range between 0 and 1. Okay, and like another way of saying looking dense is also saying that maybe S has a high computational entropy. Okay, so to be more formal, we're looking specifically for an S that has an M, so that M is delta dense, so it has measure at least delta or the uniform distribution on U. And we also would like it to be indistinguishable from S. So we'll say it's like an epsilon model with respect to tests F, and this is just the standard notion of indistinguishability. Okay. So the point is that M is actually dense, so we could kind of use to reason about S. Okay, so now we'll talk about the sufficient conditions. So the sufficient conditions are actually weaker computational entropy conditions. Okay, so the way we define, or like the conclusion of the dense model theorem says that S has a delta dense epsilon model if it satisfies the sufficient conditions. But there are other kind of reasonable ways to try to define what it means to look dense in the first place. Okay, so in this sense, the dense model theorem will basically give us like an upgrade. We'll kind of take a weaker notion, or a set that satisfies a weaker notion of computational entropy, and it will tell us, it will give us, it will be able to give us a stronger notion of computational entropy that S satisfies. Okay, so basically we're going to have these parameters. So the entropy conditions will be with respect to parameters f prime and epsilon prime, where f prime is like a new test class based off of f, and we just define it in terms of a function g. So we just take like any k elements of f and compose it with g. And two kind of important examples for us are like a product and the majority of k bits. Okay. Okay, and it turns out basically that there are two weaker notions of computational entropy which suffice, you know, to obtain the conclusion. The first, and this is the first one that appeared. So I'm not going to define it formally, but it just says that the set S is dense inside of a pseudorandom set. Okay. And this was due to Tao Ziegler, and Gowers also gave another proof of it. And the parameters, in order for this to be true, we need to take epsilon prime to be like exponentially small in the other parameters, but we can take f prime to be like a product of functions in f. And so it'll be a product of k functions in f, but I'm going to kind of not really care about k. We can just think of it as like polynomial in like 1 in epsilon and 1 in delta. Okay. And I'll mention, like, so it's kind of important that f prime is just a product, because you know, it's not clear if they would have been able to establish kind of the pseudorandomness conditions they needed if it was more complicated than that. Okay. So the second definition, or the second sufficient condition, which originally appeared in Reingold, Trevis, and Tulsiani and Vidal, it kind of enjoys a better dependence for epsilon prime. So now epsilon prime can be just some polynomial in epsilon delta, but f prime needs to now be kind of a majority of elements in f. Okay. And the second condition, I'll just say, so one name for it is metric pseudoentropy, but you can just understand it to mean that like every f can be fooled by some model which depends on the function. So specifically, like, you know, so I give you an f and you get to design an m which is supposed to be indistinguishable from s by f. Okay. So we were interested just in understanding, you know, if the kind of tension between epsilon prime and f prime is necessary here. So like we can see that, like, if we want to take epsilon prime to be larger, like in the second application, then we need to take f prime to be more complicated. And if we want f prime to be simpler, it seems like we need to take epsilon prime to be smaller. Okay. So we're able to basically show that's true in a couple of different we're able to show that this tension is kind of inherent in a couple of different cases. So kind of informally, we can show that either epsilon prime is going to be tiny or f prime is going to be complicated in some way. Okay. So more specifically, like, we can show that the dense model theorem will be false in AC0, so constant depth circuits, starting from either of the sufficient conditions if we assume epsilon prime is like polynomial. Okay. And we can also show that the sufficient conditions themselves are inequivalent with respect to a couple of different test classes like AC0, low degree polynomials, and kind of a more, and there's kind of a more general condition on the test class we can get by using a result of Schulte-Landiola. Okay. Okay, so that's basically all I wanted to say about the result, and I'll say a couple of final notes. So first, by kind of a reduction of Impagliazzo, these results imply that the hardcore lemma from circuit complexity can also fail. So previously, this was kind of known, like so Lu, Tsai, and Wu showed that like black box proofs of the hardcore lemma can be used in some sense to compute majority. But this is kind of the first explicit example, at least that Russell and I are aware of, where the hardcore lemma is actually just false. Okay? And then I'll mention another question which may appear slightly unrelated. So this is kind of in the context of de-randomization, where we want to construct pseudo-random generators. And an interesting idea for doing that is, which appeared in Sudan, Trevisan, and Vedon, is to basically generate pseudo entropy in some sense, and then extract randomness from it. Okay. So the problem with this is that we would actually need to we need the strongest notion of pseudo entropy, this idea of having a dense model in order to do the extraction. And now we know that kind of doing the conversion from the weaker notion to the stronger notion requires majority. So the question is kind of like, could this framework work in a circuit class below majority? So say, for example, like AC0 with parity gates. Okay, and this is kind of in contrast to Shaltil and Viola, who showed kind of another way of constructing pseudo-random generators, or another kind of step in constructing pseudo-random generators requires majority, which is Hardin simplification. Okay, and that's it, and thanks for listening.
Thank you, Sam. Is there any quick question for Sam? Yes, Salil, go ahead.
Okay, this time I'll actually ask a quick question.
Yes.
Can you just say a little bit more about what you mean with the phrase "can fail"? You mean you give a function, you give a
exactly, yeah. Yeah, we give a distribution which satisfies the sufficient condition and doesn't satisfy the conclusion. Yeah, so it's just false. Yeah.
Great. Thanks.
Thanks again, Sam. So stop sharing the screen so the next speaker can set up. And our next talk will be on getting a cubic formula lower bound for an explicit function in AC0. Who is giving the talk?
Hi. Hi, yes. So I'm giving the talk.
Oh, yeah, Vishal. Please go ahead. I didn't see you.
Thank you. So this is a joint work with Yuval Filmus and Or Meir. Right. So we are talking about Boolean functions in this talk, and the model of computation is the Morgan formulas. These are binary trees with OR and AND gates, and we have variables or the negation at the bottom. And two complexity measures that we care about regarding formulas are the size and the depth. So we denote by L of f the minimal number of leaves in any formula computing the Boolean function f. Note that there might be several formulas computing the same function f. And similarly, we denote by depth of f, or d of f, the minimal depth of formula computing f. And depth is motivated because it really captures the parallel time, the time that it takes the value, this formula to compute the output. If you think of all these things as working in parallel, then the depth is really the time it takes values to propagate from leaves to root. And it turns out that studying depth and studying size is essentially the same because of this beautiful connection due to Shapira that showed that the optimal depth up to a constant is log the optimal size. Okay, so this brings us to the main open question in this field of study, the P versus NC1 question. Does every language in P that can be solved in polynomial time can be solved in logarithmic depth, or in other words, in logarithmic parallel time? This is too good to be true. We don't believe this to be the case, but we don't know that this is false. Equivalently, we can ask whether everything in P can be computed by polynomial size formulas. So as I said, there's like a big gap between what we believe and what we can prove. We believe that some problems in P require exponential formula size or linear depth. These are problems that are sort of intuitively are inherently sequential and cannot benefit from running it in parallel. However, we don't know how to prove that, and the best that we can prove is that some problems require n cube formula size, and we will see the specific problems that require n cube formula size, and we will see more problems that we show in this work that requires for n cube formula size as well. Okay, second interesting question that is motivating by the P versus NC1 question is this question about composition. Let's say that we have two functions, f and g, and we take their composition. What do I mean by that? So these are Boolean functions. So to take the composition, I need to take several copies of g. I'm feeding each copy with a distinct set of variables, and then I'm taking all the outputs and feed it into f. So the natural question is, what's the formula size of this composed function? And quite obvious from the picture, the formula size of the composition is at most the formula size of f times the formula size of g. We just take the formula for f and replace every leaf with a formula for g. And the question is whether or not this is tight. This was posed in this seminal paper by Karchmer, Raz, and Vigderson. And they conjecture that indeed this is tight. Moreover, they showed that if this conjecture is correct, then they came up with an explicit function that requires a super polynomial formula size, meaning that they showed how, given this conjecture, you can separate P from NC1. I want to mention that a notable special case of this conjecture is when G is just the parity function, and it is known that this special case is correct. And based on that, we can get the n-cube lower bound. Okay. So let me tell you a little bit more about this n-cube lower bound. The essential property that is used in this lower bound is the shrinkage of formulas under random restrictions. Let me give you first an example. So here's the formula from the first slide. And now let's fix x1 to be the constant 0. This makes these two leaves a 0 and a 1. But now we notice that we can actually simplify this formula further, because 0 and something is 0, and 1 and x3 is x3. So we can simplify it further to this thing, and even further to just one leaf. So we see that the formula of size 4 with 4 leaves became a formula of size 1 after a restriction. And this is not a coincidence. It turns out that any formula shrinks under random restriction that fixes most of the variables, and the factor of shrinkage is roughly n squared. So you take any large tree and you fix most of its variables, and you get a tree which is of size smaller by a factor of n squared. On the other hand, Andreev came up with an explicit function such that after shrinkage, the formula size should be at least n, which means that before shrinkage, the formula size should be at least n cubed. In other words, in order to show that the tree is large, you show that it shrinks by a significant factor and that it is not that small afterwards. Okay, so Andreev construction is the following function. It's actually a special case of a composition. You take a composition of some hard function f0 that is on a few bits, log n many bits, and you take this composition with the parity function over n over log n bits. If you apply random restriction, each of these parties becomes something like a dictator, and you are left with something like f0. However, the formula size shrinks by a factor of n squared, so this shows you that the formula size of the original function is at least n squared bigger than the size of f0, which gives you the n cube lower bound. In other words, this is also an example that the KRW conjecture holds for this special case, because the formula size of parity is indeed quadratic. Okay, so I proposed one proof technique to show formula lower bounds. There's another proof technique. Okay, so this first proof technique that I mentioned is random restriction, and this is a bottom-up technique. We sort of saw what happens to the leaves, and somehow from the leaves we went up, right? So it seems that like sub-formulas became smaller formulas, and we didn't really touch the top part of the formula. There's another approach, which is a top-down approach, using the KW games, or Karchmer, Vigderson games. This was suggested in this seminal paper of Karchmer and Vigderson. They suggested rephrasing of this question of formula depth in the language of communication complexity. You can write a game between Alice and Bob. Alice gets an input x such that fx equals 1, and Bob gets a y such that fy equals 0. And the goal is to find a coordinate I such that this xi is different than yi. And it turns out that protocols for this game correspond, as a one-to-one corresponds with formulas for the function. And the size of the protocol tree is the same as the size of the formula. So this is really the same question in a different language. And this is really a top-down approach because naturally, when you talk about communication, you start with the root and you go down to the layers. Okay. So it turns out that the top-down approach are very useful in proving lower bounds in the monotone setting, and they also seem to be promising towards the KRW conjecture, in particular, proving intermediate results towards it. And recently, Dinur and Meir also gave a new proof using the language of communication complexity for the n-cube lower bound. So it seems that everything that we can do in the bottom-up setting, we can also do in the top-down. And this motivates the question, are top-down techniques superior to bottom-up techniques? This problem that we came up with is, can you prove an n-cube lower bound, not just for any function in P, but for a function that is in AC0, which is like constant depth, unbounded Fannin circuits? It seems, on one hand, that the techniques by Dinur and Meir could be extended to this regime. So we were hopeful to prove it using Dinur-Meir's framework. And we were also certain that random restriction techniques would not be able to prove this result. And the reason for that is that random restrictions have the property that they make any function in AC0 constant with high probability. What does it mean? It means that after the restriction, the function is so simple that I can just compute it by a constant, simply a constant function or size 0 formula. So I cannot really get anything, at least superficially, I cannot get anything from random restriction techniques against functions in AC0. Turns out that our intuition was false. And we are able to prove this result using random restriction techniques, but we're not using the standard random restrictions, but rather random restrictions that are tailored to the hard function. Okay, so this is our main result. We've proved n-cube lower bound for a function in AC0. The function is a variant of the Andreev function. Notice that this is a very similar picture to what we saw earlier, but I'm replacing the parity function with the surjectivity function. This is necessary since parity is not in AC0, so I must replace surjectivity. And surjectivity is a well-studied function that can be computed in AC0 and requires quadratic formula size. We are able to show that this function requires, like this composed function requires cubic size. And in particular, we showed that the KRW conjecture works when we compose any function f with the surjectivity function.
Avishai, you're quite a bit over time.
Okay, so this is just the last slide. Can I just finish my last slide?
Well, in a few seconds, yes.
Okay, so I just want to mention that our proof uses tailor-made random projections in a sense that the random projections are not independent projections that pick everything independently at random, but they maintain the structure of the function. They are tailored to the structure of the function. And on the other hand, they also shrink the formula, and we need to keep a balance between these two properties, which is where most of the analysis goes into. This is inspired by the work of Rossmann, Servetti, and Tan that did something similar to separate depth D from depth D plus 1. Okay. Yeah,
thank you, Avishai. Thank you very much. And also thank you very much to all the speakers. Now we have a bit of time, or actually as much time as we want, to have follow-up questions. I would like to start with Salih's question to Madhur about, can you remind us what was your question to Madhur, Salih?
Oh, I mean, maybe Madhur will rephrase it better than I asked it.
Okay.
So I'll just...
Sure. Madhur, want to, if you remember this question, can you answer it?
Yeah, sorry. So, if I understood correctly, you were asking this sort of relation between edge and vertex variable version and how it shows in expander codes versus how it shows up in here. So, I mean, okay, the way it kind of shows up in expander codes, if I understood correctly, you're maybe referring to like Tanner codes or something, where the vertex is a parity check and edges are variables. So there, I mean, one reason to do it is, of course, that you want dimension arguments, so the number of vertices is less than the number of edges. But if you do it the other way around, it's not clear how to prove things are non-empty. There is some connection, though, in the sense that if you think of triangles, they do form parity checks on the set of edges in a high-dimensional expander. And the fact that this gives a nice code is something that we do use. Although here, the number of triangles is actually more than the number of edges. So the triangles are always parity checks. It's just whether the variables are on edges or vertices. And the fact that this code is even non-empty is not so obvious. In fact, this is and this is used in proving the soundness in our construction. It's and somehow the fact that you can get these sort of things is the cohomological expansion or co-systolic expansion property of these. So there is some connection because of this parity check, but it's slightly different. But this is the extent to which I understand it.
Great. Thanks, Madhur.
Thanks, Madhur. So actually, I have a question for William about the model of permutation branching programs that you work with. So I could see that requiring, so that you cannot allow arbitrary final states to be accepting, because otherwise you could recognize it. So an arbitrary function would be sort of computable that way. But what if you at least allow like a constant number of accepting states? Would you get something similar to the known results for constant width permutation branching programs?
Sure. Yeah, good question. Yeah, so if you have a program that has a few accepting states, like let's say A accepting states, then you could write that as a sum of A many programs, each with one accepting state. And so what that means is that our pseudorandom generator does automatically fool programs with several accepting states. It's just that the error grows with the number of accepting vertices.
Okay.
So a constant number of vertices we can handle fine. But once you get up to like polynomially many accepting vertices, then we're not getting any more, any improvement, you know. Well, yeah, I mean, we don't know what the situation is once you have like polynomially many accepting vertices, we don't know what the, what the optimal seed length would be.
Is there a simple example of a function that cannot be computed by a permutation branching program of unbounded width and one accepting state?
Yeah, that's a good question. I mean, so I guess definitely our pseudorandom generators.
Yeah. Being a
gives an
possible
example.
output of your pseudorandom generator.
Right, but that's a really good question. I haven't thought about whether there's a simple. I'm guessing there's some trivial example, but good question. I don't know actually.
Okay.
No, but more generally, right? I mean, what's the intuition? What kind of functions can these things compute? Right? I mean, these kind of branching programs, what do they compute?
Right. So I think some of the intuition comes from like the example of like hard functions that we used for our lower bounds. I think those help to sort of clarify what these things can do. So the family there is, if you consider any permutation on 0, 1 to the n over 2, so like any permutation on n over 2 bits, then there is a permutation branching program that takes as input, x comma y, and it tests whether the permutation applied to x equals y. So that's the sort of thing that you can do with this, like, with this vast amount of width, is you can do something like, read and remember the entire first half of the input and then apply some permutation and compare it to the second half of the input.
And if the width isn't that large, then this model becomes weaker, right?
If the width isn't very large, yeah, I mean, if the width is like only polynomial, for example, then yeah, I mean, then there are pseudorandom, right? The optimal seed length of pseudorandom generators gets shorter, right? If it's only polynomial width, then we're sort of in this standard regime where the probabilistic method works and things like that. So.
Thank you. Any questions for any of the speakers?
I have another question for William. So, like the example that you gave as a very small probability of acceptance, do you have, so in particular, it could be approximated by like just constant 0. Do you have examples where you can show like, that you really that you can solve it with a very large width, but you cannot approximate with small width?
Good question. No, we have the opposite. We showed actually that that any of these, like, exponential width branching programs can be approximated by a polynomial width branching program, but only on one side. We get lower approximators, but not upper approximators. And so what that means is that if we're considering hitting set generators instead of pseudorandom generators, then the hitting set generator problem for these unbounded width programs is just the same as like the hitting set generator problem for polynomial width programs. And so it's sort of back into the standard regime where the probabilistic method works and stuff like that. But the approximators only go on one side. So.
Do we know that INW cannot be a pseudo-random generator for permutation branching programs, say for polynomial width, right? But with a general subset of states, right? Like in the end?
No, I mean, in fact, I would say it seems perfectly plausible that the INW generator does fool those programs. I mean, I don't know. Good question.
Okay, the next session in the other room is about to start. The first talk would be on total functions in the polynomial hierarchy, and maybe Christos will give the talk, I'm not sure. So if there are no more questions for our speakers, I would thank them once more and close this section. Thanks, everybody. Bye. Yes. Thanks.
Ronan, if you want to stay on for a second, I think I might have some thoughts on your last question.
Wasn't there a paper by Brody or something like years ago showing a counterexample for Nissan's generator, that there's some instantiation?
I don't think it was Brody. It was one of Oded's students, maybe a master's thesis that Oded supervised.
Right.
Yeah. I don't remember exactly, but that was for Nissan's generator, and I don't think it was restricted to permutation programs.
I think it's for constant width and not permutation.
Yeah. But I think maybe for your question, all right, so it depends on what do you mean by the INW generator. But if you mean the INW generator where all you assume of the auxiliary graphs is that that you have a bound on the spectral gap, okay, then it may be possible to come up with a bad example. So something along the lines of, I think you can kind of cook it up that if your spectral gap is lambda, then basically think of these as like doing random walks on graphs, that in every step, kind of each time you do a level of INW or de-randomized square, you slow down the random walk by it, like with probability lambda, you stay in place instead of moving forward, so there's some example for the de-randomized square analysis of spectral gap being tight in the de-randomized square paper. And I think it remains tight under kind of recursive applications, which kind of says that I think that implies that if you, for example, are using constant degree expanders or using constant spectral gap in you will kind of mix provably more slowly than a truly random walk, and hence be statistically far from the right distribution. And so if you have an arbitrary subset of except for, this is just kind of guessing, but I think the answer to your question is probably the INW generator. If this is what you interpret it to be, probably can't get log n over epsilon.
Okay, so I don't want to get in trouble because I see that Russell is here, so I don't want to interpret I don't want to give the wrong interpretation. But suppose my interpretation.
Your interpretation is as good as mine.
That's very democratic of you, Russell. I also want to write like the fact that you live in a third world country where people have coups and storm the capital, right? I mean, I'm all there for you.
It happen to you someday.
But suppose my version of the INW generator was Raz Rheingold with extractors, but I'm not with spectral.
Yeah, if you start allowing that kind of flexibility, I mean, and there's some point at which there's some level of generality at which again, this is just guessing. I think there's some level of generality in the phrasing of the INW generator where if you then choose the graphs that you use at random, one can do maybe some kind of probabilistic method argument to argue that it can actually a construction of that form can actually work. I think. Again, I'm not 100% sure on that. So I think it just will be sensitive to how general you allow the construction to be.
Yeah, thanks.
Do you have in mind, I mean, an approach for proving what you just suggested, that if we pick if we use random graphs instead of expanders?
Yes, that's what I meant by the problem. Yes, exactly. Random graphs, and you don't go all the way down to the level of bits. Maybe there's some. Maybe you don't reveal the entire. Let's see if I remember correctly. This is a kind of very long time ago. Played around a little bit with things along these lines, but this is all just kind of guessing answers to your question, Ronan. It's someone should actually try to work it out.
Yeah, thanks. It's very. So is there any hope to use these techniques for like standard, or if there is such a thing as like standard permutation branching programs with fixed width, with like some width larger than a constant?
Yes, I mean, it did already give new results for like the polynomial width case under this assumption of one accepting vertex.
No, but suppose I don't want this assumption of one accepting vertex,
right?
And but I give you a budget of right, and I only want you to do more than constant width. So are these techniques, do they seem helpful?
Yeah. So I mean, if it's like logarithmic width or something, right? Then in particular there are only logarithmically many accepting vertices, and so you just pay a factor of log n in the error of the program, and so.
So maybe it's worth mentioning. So if you take that arbitrary permutation branching programs with any number of accept vertices, and you don't care about having a generator, but are willing to do a non-oblivious, estimate acceptance probabilities, that we know how to do. That was kind of the previous paper from Fox that we build on for the generator. That can do that with nearly logarithmic in nearly logarithmic space. So do what you would be able to do, and even better in terms of epsilon than you would have with an optimal PRG. And so a question is an open question, though, is whether you can get that better, handle the many accept vertices, or get better dependence on the error in an oblivious like PRG like way.
Thanks. And it's great seeing you guys.
Likewise.
Yeah, you too.
All right. Bye, everyone. Oh, I should introduce Ted. Ted also co-author on the paper. Ted, Ronen, Avishai. Ted's an undergrad at Harvard.
Everyone. Nice to meet you. I think
Thank you for all the great comments.
Yeah. It's right. I mean, it's 12:30, right? In the after midnight in Israel.
It doesn't look like it behind you. It looks sunny.
Yeah.
Sunny and windy. Where is it from?
So how is this possible? You're not in Israel, I guess.
No, it's virtual background.
This is a virtual background, right? And right, like for people who don't know, who don't read Hebrew, I can reveal where Abishai is.
I used Google Translate already.
Yeah, it's not a challenge anymore, right? Yeah. Elon was asking me if I'm in a spa. I was answering him.
No, I mean, I could show you the back of the room, but I'm sitting in this like very small, like kind of basement room with a lot of laundry behind me. So I'm trying to hide it. Right. So.
All right. Well, good night then, Ronen.
Bye. Good night.